Okay. Am I live? Am I audible? Students, let me know in the chat box. Hi everybody. How is everybody doing? How much pressure is on you right now, guys? Let me know in the chat box. Hello everybody. Can you hear me and see me clearly? Just let me know that. Hi Kavi. Hi Tarini. Hello. Can you hear me and see me clearly? So we'll begin this very packed session. We're going to cover the organic chemistry in one day. So what all you need to know to approach maximum questions in organic chemistry in just one day, we're going to do that. We're going to start from the hybridization, right? Okay, you can hear me. Hi everybody, hi. Chalo. So we're going to start from the hybridization and then we're going to go what are the rules for IUPAC nomenclature. Always remember IUPAC is again very importantly asked in your JEE exams every year, and then will come all the various orders and the effects that we study, right? What are the aromaticity effect? And then after studying all the inductive, mesomeric, resonance, hyperconjugation, all these effects, how are these effects actually affecting your acidity order, your carbocation stability order, your carbanion stability order, and at the end we're going to also learn about the SN1, SN2 reactions. What are the differences between the two? What solvent is essential for SN1? What solvent is essential for SN2? All of these things we're going to study today, and also at the end we're going to practice loads and loads of questions along with the reagents which are very common in your organic chemistry exam. Chalo, let us begin this session. Are you guys ready? So before that, again, I have to share with you guys, whoever students are joined with me right now and are preparing for the JEE 2025 already, then I have a very good news for you guys. If Vedantu is offline now, you can join any of these centers, any of the cities that are mentioned here, right? If you belong to these cities or you belong near these cities, you can go check the Vedantu offline center out. How to know more details about it? You can call on this toll-free number, or even you can reach out in the link in the description box below. Write an email to us, write a message, comment, whatever. You can reach out to us and you will be enrolled in the Vedantu learning program. And why is it 1 in a million program, bacha? Because we are guaranteeing improvement in your marks, otherwise 100% free fee refund. Right, so this is like a win-win chance for you guys. You should definitely grab it if you're preparing for the JEE or NEET 2025, whatever exam that you're aiming for. Chalo, let us start with the very first topic, which is your hybridization. Let me also look at the chat box. Okay, beta duration of this session would somewhere be around 2 to 2.5 hours. I will try to complete maximum of the things that you need to know before your organic chemistry paper. First thing that you should know is the hybridization. You all are very familiar what is the hybridization of carbon here. So when carbon bacha is attached to 4 atoms, its hybridization is sp3. I'm going to start from the very basics, right? This is sp3 carbon, everyone is aware of that. Now when carbon is attached to just 3 atoms, 1, 2 and 3, then it is called sp2 hybridized. Similarly, when carbon is attached to just 2 atoms, it is called bacha sp hybridized carbon. Isn't it? Is this thing clear to everybody? Now what happens in the case when I change the atom in the question? If I take, for example, if I take nitrogen instead of carbon, what will be the hybridization of nitrogen in that case? So nitrogen bacha, when it is attached to just 3 atoms, attached to 3 atoms, right? 3 separate atoms, then bacha, its hybridization is sp3. Understand this thing. Similarly, when nitrogen is attached to 2 separate atoms, its hybridization is sp2, right? What about oxygen or oxygen family? So bacha, when oxygen is attached to 2 separate atoms, then bacha, its hybridization is sp3. So you need to know all these things. right? Understood all these things? When nitrogen is attached to 3 atoms, its hybridization is sp3. When nitrogen is attached to 2 atoms, its hybridization is sp2. And similarly, if oxygen or the family of oxygen like sulfur is attached to 2 atoms, then its hybridization will be sp3. So you have to understand these terms, that as the atom changes, the hybridization also changes. What is the other thing that you need to know? Is the electronegativity order of hybridization. What is that order? That sp hybridized atoms are the most electronegative, then will come your sp2 hybridized, and then will come your sp3 hybridized atoms. So this is the electronegativity order, which means what? How do you understand it? How do you keep it in your brain? For example, which is the most electronegative element you know? It is fluorine, right? Fluorine is so electronegative that it keeps electrons to itself. Which charge is stable on fluorine? On fluorine, just how on fluorine negative charge is stable. Similarly, on your sp hybridized atom, negative charges will be more stable because they are more electronegative in nature. All these things you will use while you are doing the application part in the GOC. That's why I'm explaining these things to you from the very, very basics. Is this thing clear to everybody? Got it? Got it? Next, we're talking about nomenclature. So we're not going to talk in very detail about nomenclature, right? Instead, what I'm going to do, I'm just going to tell you what is the order that is followed. Because right now, I'm expecting that your exam is just in 3 days. I'm expecting you know what nomenclature is, how do you name the compounds. But one thing that you can forget is the priority order of the functional groups that need to be kept in mind while doing nomenclature. So what is the priority order? It is COOH gets the highest priority, followed by the SO3H group, followed by the ester group, followed by the acetyl halide group, followed by the amide group, right? Followed by the nitrile, then the aldehyde, then comes the ketone, then comes the alcohol, then the thiol, then your amine, then your, at the end comes your double bonds, and then your triple bonds. So this is the priority order. Always remember this thing or take a screenshot of this. Very, very important once again. Okay, now let's move on to this question. Who can answer this question for me? The IUPAC name of ethylene chloride. Why have I included this question? Just to keep it in your mind. This is once again JEE Main 2022 question. Why is this question important? Because here a common name is given to you. So common names, whichever common names you come across while doing JEE questions, you need to make a list of all those common names, right? Because common names are very commonly asked in JEE exam. I'm again and again telling you, try to answer this question for me. First answer I've received is by Kirti. Kirti has answered A. No, but it's not A. It's not A. Sharvesh has answered C. Sharvesh has answered C. Again a wrong answer. No, bacha. The name here is ethylene chloride. Ethylene chloride, bacha, is the name of this compound. Ethyl means 2 carbons, so I'm going to make a 2-carbon chain, right? And when 2 chlorines are on the same carbon, right, this kind of compound is called ethylene chloride. So what is the IUPAC name of this compound? 1,1 dichloroethane. So the answer is D. So ethylene chloride, bacha, is your geminal dihalide, isn't it? It is a geminal dihalide. This is given in your haloalkanes and halogenes chapter of your NCERT. If you are doing the grave mistake of not following NCERT, even for your JEE exam, you are in big trouble, bacha, because in your JEE NCERTs, once again, for chemistry is very, very important. Okay? This is a geminal dihalide. But if the name was something like this, if the name was ethylene dichloride, right? If the name was this, bacha, then what could have happened? then its structure would have been ethylene, matlab two carbons, and when both the chlorines are on separate carbons, then it is a ethylene dichloride. So this is the common name for ethylene dichloride. Understood this thing? So this is what kind of halide? This is a vicinal dihalide, isn't it? So when the two chlorines are on the same carbon, it's called geminal. And when the two functional groups are on separate but together carbons are called vicinal dihalide. Is this thing clear to everybody? So the correct answer is D. Yes, whoever answered D is extremely right. Next is the stability of order of dienes. Again, a very important topic, right? What happens in the stability order of dienes? So here, what you take, a conjugated diene is more stable than the isolated diene, which is more stable than a cumulative diene. What does that mean? Let us look at the structure. So isolated diene looks like this, where the two double bonds are very far apart, which means at least they are 2 sigma bonds far apart. Can everybody see that? Then they are called isolated diene. Conjugated diene is what? When 2 pi bonds are separated by just 1 sigma bond. Can everybody see? 2 pi bonds are separated by just 1 sigma bond. Such a structure is called conjugated diene. Now what are cumulated dienes? When both the double bonds are associated on the same carbon. This is a very unstable structure. It doesn't even exist, right? It is very unstable. So what is stability order? This conjugated dienes are very stable, followed by isolated, followed by cumulated dienes. Is this thing clear to everybody? Okay? Very important concept once again. Let us do one question on the same concept asked in JEE Mains 2022. Which of the following is an example of conjugated diketone? Who can answer this question for me? Who can answer this question for me? I'm looking at the chat box once again. Try to answer this question. Giving you 30 seconds. I'm looking at the chat box. Yes. Try to answer this, bacha. Your exam is just in 3 days. Try to answer. First answer received by Prabhu Sai Ponada D. D, okay. First answer that I've received is absolutely wrong answer. Absolutely wrong. Then Manikandan has answered. Monisha has answered. Kavi, Soumya, very good. Very. All of these, bacha, Jaya Dev. All of these have given me the correct answer. What was the meaning of conjugated? Can you see the C option over here? Here, can you see this double bond, this double bond, this double bond, and this double bond are separated by 1 sigma bond, isn't it? Wasn't that the definition of conjugated dienes? When the double bonds were separated by a single bond, that was called a conjugated diene. But here the question was about diketone. So can you see these diketo groups over here are separated by the double bonds, again by a sigma bond, by 1 single bond. Hence the correct answer is C. Can everybody see that? The correct answer is actually C, due to this conjugated system. Double bond, single bond, double bond, single bond, double bond. Understood? Okay? I am moving forward to aromaticity. Again, a very important concept. Many questions will be asked from this concept. But the applications part of aromaticity is also very important. So, firstly, let us see the basics. Then we'll move on to the applications. The basic is what are aromatic, anti-aromatic, and non-aromatic compounds. The 3 kinds of compounds in which the entire organic chemistry can be classified. So, first look at the aromatic compounds. So, aromatic compounds are always cyclic in nature. Number first point. Number second, they are always planar structure. They will exist in a 2D plane. Number third, they are always conjugated system. How to remember conjugation? That all the atoms in them will be sp2 hybridized. All the atoms in that ring, cyclic ring, will be sp2 hybridized. Okay, that's it. And if you want to learn more about aromatic, anti-aromatic, non-aromatic compounds, their applications, and want to look at more examples asked from this topic, Then I've already uploaded videos on this channel. You can go check it out under the playlist of aromaticity. Recently, I've uploaded all the videos. You can go check it out. Chalo. So for aromaticity, what were the conditions? Cyclic, planar, all the atoms sp2 hybridized, and at the end should follow the Huckel rule. What should follow? The Huckel rule. What is the Huckel rule, bacha? 4n plus 2 pi electron rule. Let us look at some of the examples. For example, benzene here has 6 electrons. So it is a aromatic system. Pyridine here, 6 electrons, aromatic system. This naphthalene here, 10 electron system, again aromatic system. Why is it 10 electron? Because they are 1, 2, 3, 4, 5. 5 pi bonds. And 1 pi bond is equals to 2 electrons, right? 1 bond is equals to 2 electrons. Hence, this is a 10 pi electron system. So, all of these are aromatic system. Now, what is anti-aromatic system? So, bacha, anti-aromatics follow all these 3 rules, which is they will be cyclic, they will be planar, all the atoms in that ring will be sp2 hybridized, but there will be one change, that the number of electrons in the ring will follow the 4n pi electron system, which means that they will follow the table of 4. For example, if they have 4, 8, 12, 16 and so on electrons, then they will be anti-aromatic system. For example, let us look at here. Here, this system is a 4 pi electron system. This system is again a 4 pi electron system. This system is again a 8 pi electron system. So, all these compounds are anti-aromatic compounds. Understood the difference between the two? Both of them, aromatic and aromatic, first 3 conditions will remain the same. Only thing that is changing is the number of electrons that they have in the ring. Now, the next thing is what are non-aromatic compounds. So, it's a non-aromatic compounds are those which do not even follow these 3 conditions, which fail. Either they will not be cyclic like this structure, right? Either they will not be planar like this structure, right? I will discuss this structure in detail. Either they will be not a planar structure, or the atoms will not be, all the atoms will not be sp2 hybridized. For example, look at over here and look over here. The atoms here are actually sp3 hybridized, isn't it? Hence, the entire ring is not sp2 hybridized. Hence, once again, this is a non-aromatic system. Understood these 3 things? Now, let us talk about the stability. So, as we know, in the entire organic chemistry, the most stable system, let's talk about the stability order, right? So, the most stable system are always aromatic system, okay? Followed by non-aromatic, right? And the least stable are your anti-aromatic system. Please remember this thing. Anti-aromatics are very, very unstable. They're so unstable that they do not even want to exist. Very, very rarely they exist in nature because they're so unstable. Understood this part? Please write down the stability order as well. Okay? Now, next is let us look at some of the non-aromatic system. So, what will you consider this compound to be? So, let us look at this compound. Is it cyclic? Yes, ma'am. Is it are all the atoms sp2 hybridized in this? Yes, ma'am. I can see all the carbon atoms here are sp2 hybridized. So, ma'am, this is a cyclic system. All the atoms are sp2 hybridized. And how many electrons does it have? 1, 2, 3, 4, 5. 5 pi bonds. Which means, ma'am, this is a 10 pi electron system. Hence, it is following the Huckel rule. Therefore, this should be a aromatic compound. But in reality, it is not. Why? Because in this compound, can you look at these hydrogens over here, which are in the middle? These hydrogens cause so much of steric hindrance. What do they cause? They cause so much of steric hindrance that this structure is no longer planar. It is actually a very twisted structure because of these hydrogens. Hence, it loses its planarity. Therefore, this is actually a not aromatic, which is a non-aromatic system. But you can convert this system into aromatic system by replacing these two hydrogens by a CH2 group over here. Now this ring becomes planar and gains back aromaticity somewhat aromatic, not fully aromatic. This is actually homoaromatic compound. Okay, understood? Now let us look at some of the more examples of aromatic compounds. So can you see naphthalene, anthracene and anthrene over here are all bicyclic or tricyclic compounds, right? And all of these are actually aromatic compounds. Why? Because they are all following the Huckel rule and all the rules of aromaticity. Okay, understand these things? Everybody understood? Now I'm moving forward to more examples of non-aromatic compounds. Now look at this compound over here. Now you will see, ma'am, you will tell me, ma'am, this is a cyclic compound. Okay. Are all the atoms sp2 hybridized? Yes, ma'am, all the atoms are sp2 hybridized. Now what is happening? How many electrons does it have? It has 1, 2, 3, 4 pi bonds. 4 pi bonds, which means 4 into 2 is equals to, this is a 8 pi electron system, isn't it? So ma'am, this should be anti-aromatic compound because this is coming into the table of 4. So this should be anti-aromatic. But bacha, this is actually a non-aromatic compound because this gains the shape of a tub. This gains the shape of a tub. Hence, it is no longer a planar compound. This is a non-planar compound because it is losing its planarity. Hence, it is gaining a non-aromatic nature. Okay, so this is actually a non-aromatic compound. Okay, you can understand this thing by keeping another thing in mind, which is this has how many carbon atoms? Approximately 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon atoms are there, which means it is a very big ring, right? It is a very big ring, and big rings have the advantage of twisting and turning their shapes. Now, bacha, here, if it was a planar structure, then it was becoming an anti-aromatic compound. And we know that, ma'am, anti-aromatic compounds are so unstable that they do not even want to exist in nature. But just like you and me, this compound also want to exist. So in order to exist, in order to survive, what it will do, it will just become a tub-shaped structure. Like now existing, because now I am a non-aromatic compound. Understood this thing? So you don't have to like mug up things, see what will happen. You just have to look, oh, a big ring. It means it will distort its shape, become a tub structure so that it can at least exist in life, right? You can just empathize with this compound, right? Because every compound wants to exist. Okay? Understood? Now, bacha, let us look at some variations of this compound. See, this variation, first variation, can everybody see over here? In this variation, how many electrons are there? This has 3 pi bonds plus 2 lone pair of electrons, which means 5 into 2 is equal to, this becomes a 10 pi electron system, right? Which is actually following your 4n plus 2 pi electron rule, isn't it? This is following the Huckel rule. Hence, bacha, this compound will be aromatic in nature. What would be the nature of this compound? This compound is aromatic, which means that it will keep its planar nature. It is not converting into a tub-shaped structure. Why? Because by not converting in tub shape, it is gaining aromaticity. So why will I convert into a tub shape structure? I will remain a planar structure. Similarly, in this case, can you see this is again a variation of this compound only? But right now, this is a 6 pi electron system, which means again following the Huckel rule. So this is once again a aromatic compound, right? Which means it keeps its planar structure because due to that it is gaining so much more stability and it is becoming aromatic compound. Is this thing clear to everybody? Is this thing clear to everybody? Okay, now let's move on to this question. Who can answer this question for me? The question is from JEE Mains 2022. Which of the following is the most stable compound? Who can answer this question for me? Very easy, basic. See, very basic questions are also asked. Stable, for stability, you will look at their aromatic character. I just told you, aromatic compounds are the most stable compounds. Who can answer this? Okay, I'm looking at the chat box. 30 seconds. 30 seconds to answer this question. First answer by Soumya is B. Soumya is saying B. Beta, look at the B structure. The B has how many electrons? The B is a 4pi electron system. This is a anti-aromatic compound, right? Anti-aromatic, which means it will not even exist. B cannot be the answer. Then I'm getting A. Who was the first person to answer A? Let me see. Was Shri Sailesh. Shri Sailesh. Very good, Shri Sailesh. This is definitely an aromatic compound because this is a 2pi electron system. Definitely a aromatic compound. This is also once again a 4pi electron system. Therefore, this is once again anti-aromatic. This is, here can you see sp3 hybridized carbons are there. So these are actually non-aromatic compounds, right? This is a non-aromatic compound. I hope this thing is clear. So the correct answer is A because here 2pi electron system is there and we know it follows the Huckel rule. Very easy, basic question. Now let us look at some of the applications of aromaticity. Once again, who can answer this question for me? Which of the following compounds will show highest dipole moment? I'm giving you a little hint, which is here also you will have to look for the aromatic character. So I'm giving you just 30 seconds to answer. After that, I will tell you how to approach these questions. This type of questions have been repeated at least 3 times in your JEE exam. Similar question, dipole based question, same type of question asked at least 3 times in your JEE. So again, a very important type of question. Okay, first answer by Naga Sai I'm receiving is D. D. Very, very good. Praveen D. Cherry D. Very, very good. Everybody is answering me correct. Wow, very good. Proud of you, students. Correct. So here, bacha, whenever such compounds are given to you and you have to look for their aromatic or anti-aromatic nature. So can you see in every compound there is a exo bond present. Exo bond. Now what is exo bond? Whenever a cyclic ring is there and outside that ring there is a double bond. Can you see? There's a double bond outside the ring. Such kind of double bonds outside the ring are called exo bonds. Right? Now what will happen in this case? How will you check the aromaticity? You just have to move this double bond. What do I mean by that? What do I mean by that? 1 second. Let me rub this. Okay? What do I mean by that? Here, try to form a dipole out of it. So because oxygen is more electronegative, so this will get a delta negative charge on this, right? So therefore, this here will get a delta positive charge, isn't it? Isn't it? Okay? So here it gets a delta positive charge. Now count the number of electrons on this. This has how many electrons? This becomes a now 2pi electron system, isn't it? After breaking that bond, this becomes a 2pi electron system and all the atoms are also sp2 hybridized cyclic system, planar system. Hence, this becomes the aromatic system. The correct answer is A. A. Okay? The D is not the correct answer, sorry. A is the correct answer. Okay? Now look at other compounds. Can you see that this is gaining the aromatic character? And we know that after breaking this double bond, okay, understand one thing. Once I'm breaking this double bond, what I'm forming? A positive and a negative charge. A positive and a negative is called a dipole, right? And it will remain in such a position because after creating a dipole, this ring is gaining a aromatic character. Hence, this will definitely show highest dipole moment. So, because it is gaining stability after that. So the correct answer is A. Now let us also check the other options. Here can you see this cannot be aromatic because this carbon is sp3 hybridized and out of the race because aromatic compounds are the most stable. No other compounds can be more stabler than aromatic compounds, right? Now again look at over here. Once again this carbon and this carbon are once again sp3 hybridized, again out of the race of aromaticity. isn't it? Now, bacha, here what can happen? Here, if I try to break this, then oxygen will get the negative charge. This carbon gets a positive charge, right? Again, oxygen will get the negative charge, and this carbon, why is this not working? This will get the positive charge over here. Now count the number of carbons, number of electrons. This is now becoming a 4pi electron system, which means anti-aromatic, right? So this will be the most unstable system. So this will never form the dipole, because after forming the dipole, I am becoming anti-aromatic. I am becoming a very unstable system. So this can definitely never be the answer. The correct answer is first. For the dipole moment, what you have to do, if there is a double bond outside the ring, break that double bond. And after breaking a double bond, if your cycle is gaining an aromatic character, then that will show the highest dipole moment. I hope this thing is clear to everybody. Is this thing clear to everybody? Okay. Let us move on to the next question. Which among the following is the strongest acid? Once again, you have to look for the aromatic character. Why am I saying that? What is meant by the strongest acid? Strongest acid is that which gives away H plus easily, right? Which gives away H plus easily is the strongest acid. How will you judge that which compound will give H plus easily? Is when after giving away the H plus, the anion formed should be stable, right? So it depends upon the stability of the anion formed after the H plus is leaving. Understanding this thing? Now what will happen in this case? I have received B, B, C, B, C, 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 B, so many C, B, C, B answers. Okay. So whoever has answered C are absolutely right. Please clap for yourselves. Okay? Here what will, no. C is not the answer. Sorry. Whoever has answered C are absolutely, let me show you how to approach this before confirming the answers to you. Now see whoever is answered. What can happen? If I take away H plus from here, then what will happen? This minus sign will remain over here, right? Now count the number of electrons on this. This is actually a 4n pi electron system, isn't it? So this becomes a anti-aromatic system. After I give away H plus, the anion that is remaining is becoming into an anti-aromatic system. So why will it give away H plus? After giving away H plus, I am becoming so unstable. Why will I do that? I will keep my H plus to myself. I will not give it away. But look at the D compound. Here, if the H plus goes away from here, then the negative charge formed over here. Now count the number of electrons. This is now becoming a 6 pi electron system, isn't it? 6 pi electrons, we know, ma'am, this is a aromatic system. And aromatic systems are stable. So understand in D option what is happening. As soon as I'm giving away my electron, my H plus, I'm becoming a very stable system. So why will I not do that? Just go away from my house, because after that I'm becoming a very stable system and I want to become that. Hence the answer is D, right? It will easily give away H plus because after that it is converting into a very stable aromatic compound. And B will not be the answer. Why? Because if you are comparing D and B, then aromatic systems are more stable than if I create an anion over here, right? This is more stable than this system. Understand this, right? Because aromatic systems are the most stable. Here, how will you count the stability? That, ma'am, this is undergoing resonance. But resonance comes later on in the order of stability. Aromatic compounds will always be the hierarchy of stability, will always be at the top of stability. If there is a tower of stability, right? Aromatic compounds are the most stable. Then below that will come the resonance compound. Resonance stabilized compound. Okay. And then below that we will just talk about in a certain while. Is this thing clear to everybody? Chalo. Next question. Okay, next question is not there. Now we're going to study about the electronic effects. Number first electronic effect that you all should know is the inductive effect. We all know there are two types. the plus I and the minus I effect. What is the plus I effect? Whenever we are adding the atoms which are donating electrons, right? For example, here is your R group. So any group which is donating the electrons to the R shows the plus I effect. Now what are minus I effect? Minus I effect are those which are pulling away electrons from your alkyl chain. Understood this thing? Plus I is donating electrons and minus I is pulling electrons towards itself. Now let us see what groups show what effect. Plus I is donating electrons. To donate electrons, it must be very obviously rich in electrons. So what will be the order of that? So whichever has a negative charge on it. First of all, if I have a negative charge or a lone pair of electrons on me, I can easily donate electrons, right? So should be electron rich. So can you see CH2 minus is has the more minus plus I effect than your NH, than your oxygen. What does that mean? It means one thing, bacha. Okay, let's compare the electronegativity order of carbon, nitrogen and oxygen. We know that, ma'am, oxygen is the most electronegative in this series, in these three atoms, right? So whichever atom is most electronegative, please keep that in mind. Most electronegative atoms will keep the electrons to itself. They are so negative, they don't want to give away their electrons. So instead, carbon will give away its electrons easily, right? Because it is not that electronegative. Hence, carbon with the negative charge comes first in the race of donation of electron. So carbon over here will easily donate electrons. Why? Because it is less electronegative than oxygen, than nitrogen, hence easily give away electrons, right? So CH2 minus, then NH minus, then O minus, then followed by COO minus, then your tertiary alkyl, secondary alkyl, primary alkyl, then this is the trend followed for your plus I series. Understand this thing. Tertiary alkyl means what? For example, this is the tertiary alkyl group, right? So tertiary alkyls give more electron, donate more electrons than your secondary alkyls. Secondary alkyls look like this, isn't it? Isn't it? So if you want to compare between tertiary and secondary, because tertiary has more R groups, more the R groups, more the electron donation capacity. Understand this thing? And this trend is very, very important. Take a screenshot of it, or I'll send the PDF. You can just check it from the PDF. Now the minus I series. Minus I means what? Which are pulling the electrons towards itself. Okay? What can be those groups? Those are the positively charged species. First of all, can you see? NF3 plus, NR3 plus, NH3 plus, right? All those which has a positive charge on it will pull the electrons towards itself. Now next is all, and after the positively charged, how to just identify the minus I series, bacha? They will definitely have a multiple bond in them. For example, look at the NO2 group. That's a neutral group, right? After the positive, how to identify neutral groups? NO2 groups looks like this, right? It has a double bond in it, right? Similarly, your CN groups is C triple bond and again a multiple bond in it. Similarly, your aldehyde group, your acid group, okay? All of these groups have multiple bonds in it, and all the multiple bonds group will definitely show the minus I effect. Okay, understand? This is like a trick of funda you can use. After that, all the halogens, because these are so electronegative, they will pull the electrons towards itself. So these are again showing minus I effect. Then your OH, OR again, because oxygen is a electronegative compound. Then your triple bond, because here the carbon is once again sp hybridized, as I told you. sp hybridized are more electronegative carbon. Just like oxygen is electronegative, it is pulling electrons to itself. Similarly, this will also pull electron towards itself. Then the phenyl ring, strained ring and hydrogen. Understand, this is a very important trend. You should take a screenshot of it, right? Right? Now, I am moving on to the next thing. So, these are some of the characteristics that you should know, because there are so many Assertion, reason, question asked on such topic. That is inductive effect a permanent effect? Yes. Okay, and what kind of electron shifting takes place? Sigma electrons are shifted, right? So all these you can read on your own. The proper thing that you can use in examples, I've already explained it to you, right? Now next is the resonance effect. In resonance, bacha, what happens? For example, look at this compound over here. How will it show resonance? Here the oxygen has lone pair of electrons. So it can donate the lone pair of electrons over here, and then this double bond moves over here. So this movement of electron within the molecule is called resonance, right? So this is getting its own resonating structure. Everybody is familiar with resonance. What is happening? The lone pair gets converted into double bond, and the double bond gets converted into lone pair. Basic funda of resonance. Now let's talk about various types of resonance that are available. So I will tell you very quickly how to quickly identify the resonating structures, whether they are present there or not. Number first identification is, bacha, for example, here there is a double bond over here. And right next to the double bonded carbon, right next to that carbon has a positive charge on it. So this will also definitely show resonance. Can you see? This double bond can go over here and the positive charge goes over here. Okay? And now if the question comes, which one is the true molecule? Which one is the exact correct structure of this molecule? Then bacha, the correct structure whenever a compound has resonating structures is definitely a resonance hybrid of all these three. Understand this thing. This is the true molecule where both the bonds have partial double bond character. This is a true structure. Neither this nor that is a true structure. Only this resonance hybrid will be the true structure in all of the cases, right? All of the resonating structures cases. So number first case of resonance is right next to the double bonded carbon, there is a carbon with a positive charge. Will definitely show resonance. For example, this can also be applied to the benzene ring, right? Benzene ring, this carbon has a positive charge on it. So right next to the double bonded carbon, the carbon next to it has a positive charge. Then this will definitely again show resonance. And what is the true structure of this? This resonance hybrid is the true structure of this compound. Now once again I'm telling you one more thing, that more the resonating structures, more stable will be the compound. So stability will depend on so many factors I will discuss in just a little time. First of all, just let us know what types of resonance are there. Then I will discuss on what factors the stability depends. So can you see this has so many resonating structures, while this had just two resonating structures. Understood this thing? We are not going into too much detail because this thing I am assuming that you know how the arrows move, how the pi bonds move, because right now we cannot spend so much time in just getting explained this thing, but you can see and just recall all your concepts. Now the third example which are here given once again, what is happening? There is a double bonded carbon, and right next to that double bonded carbon there is a positive charge presence. Here again the resonance will be present. Can you see? This has three resonating structures, right? Understood this thing? So this is more stable than the first compound, right? Because it has three, the previous one had around six. Usse pehle wala had just two resonating structures. Okay? Next kind of resonance is shown by what? When along with the double bonded carbon, the carbon right next to it has a free radical. This will again definitely show resonance. So number first was, along with the double bonded carbon, the carbon had a positive charge. Here, right next to the double bonded carbon, the carbon has a free radical. Again showing resonating structure. This bond will again move here and the free radical moves to the last position just like that. And this resonance hybrid will be the true structure of this compound. Similarly, the similar can happen with the benzene ring. Here once again, the carbon to which the double bond is present, the carbon right next to it has a free radical. Here once again what can happen, this can move over here and the free radical moves over here, and this can get so many resonating structures like this. So the next criteria was a double bond and a free radical. Understood? Next, how will you identify a double bond and a negative charge over here. Can everybody see? A double bond and the negative charge. Once again, this bond can move over here, the negative charge can move over here. Once again, will definitely show resonance, right? And the fourth and the last type is when along with the double bonded carbon, the carbon next to it has a lone pair of electrons. Similarly, the carbon, the atom next to it has a lone pair of electrons. To the double bonded carbon, the atom next to it has a lone pair of electrons. In all of these cases, these will show resonance. These will show resonance just like this. So all of these will again show resonating structures. So you understood what were the four key factors. A double bonded carbon and the carbon next to it can either have a positive charge, a free radical, a negative charge, or even your lone pair of electrons, right? 4 types of resonance, done and dusted. Now let's talk about their stability. Yes, bacha, now I'm going to see the chat. Beta, what is your question? Yes, bacha, tomorrow we are definitely doing the paper of chemistry. We're definitely solving some questions tomorrow. Let us do this example. Who can answer this question for me, right? Along with answering this question, I'm going to answer some more concepts about the stability of resonating structures. How do you determine? First thing I told you, more the number of resonating. Okay, I'll write this on another page. Okay, I'll write this on another page and we'll solve the example over here, right? We'll solve the example over here. I'll write it here. Okay, we are talking about the stability of resonating structures, right? Number first, bacha, the stability depends upon one thing. One thing is that the neutral compound, neutral molecule will be the most stable molecule. Understand this thing, which means the molecule which do not have either one positive or negative charge will be the most stable molecule. Okay. Next is, bacha, this is the neutral molecule will be the most stable. Next is when you are moving the negative and positive charges, right? Then the negative charge is most stable or electronegative atom, right? For example, if on oxygen, if the oxygen is getting a negative charge, that will be a more stable resonating structure. But if carbon is getting a negative charge, that will not be a stable resonating structure. Similarly, if oxygen is getting a positive charge on it, once again, not a stable resonating structure, right? So we are going to rate the stability. Number first, neutral molecule. Number second, when we are moving the charges, the negative should go on the electronegative carbon or atom and positive should go on the electropositive atom. Understood? Now the third point is, whenever you're moving the positive and negative charges, then the separation of charges should be minimum. Understand this, right? For example, the positive and negative should stay together. How much together they are, they will be the more stable structures. Understand this thing. Now try to answer. Okay, and the last thing was, more the resonating structures, more stable will be compounds. So those were the 4 rules. More the resonating structures, more stable will be the compound. Understood this thing? Now answer this question for me again. What do you think should be the order of stability of resonating structures? 3 structures are on your screen. Try to answer. I'm again giving you just 30 seconds. Just 30 seconds. Beta, the tricks I will teach you right now, how to approach your... Somebody is asking them, what are the tricks to approach organic chemistry questions that we don't know about? I'm going to teach you the exact tricks. How to identify the reagent at the molecule, where the attack will happen, where it will not happen. I will definitely teach you all those things and you'll be clear in your head. Just stay with me. ठीक है? ब्लर हो रहा है. Why does it happen in my class? I don't understand at all. I do not understand at all. Why is this happening? 1 second, let me check the camera. Is it okay now? Why is this happening? Yes. Blur. Why is it? I don't know why does this happen in my class. Oh my God, I'm so tired of it. ठीक है, try to answer this question for me. We'll see if it doesn't get blurred after a while. After a while, it won't get blurred. We will just look to that. Okay. Can you see that now? Why is it happening? I don't know. Okay, now it's okay now. If I'm standing here, it is okay, right? It is okay now, na? Let me know. If I'm moving too much, it is not okay, है ना? So I will just stand here and teach you. ठीक है? ठीक है? चलो. Okay, first answer received is ACB. Okay, let us see. I told you that the neutral molecules are the most stable. So the A molecule is neutral. There is no positive negative charge separation. So first will be the most stable. Next, let us see. Can you see third and second? Can you see in second in third there is a positive charge on oxygen, isn't it? Hence, the positive charge cannot be stable on oxygen. So therefore, this structure, but again, there is so much more separation of charges on the second one, right? Right, bacha? Here. So what can happen? The correct answer is 1, 3, 2. I'm trying to not move. Why? Because can you see that there is so much of separation of charges in the second? The positive and the negative are too far apart. While in the third, what is happening? The positive and the negative are not that far apart. So this is the final order because separation of charges also matter when we are talking about the stability order. Right? Right? Understood this thing? Yes, very good. Now next thing that we're going to talk about is the extended and the cross conjugation. What happens in that case, bacha? What is cross conjugation? Whenever you see double bonds like this, these are conjugated double bonds, right? Can you see double bond followed by single, double, right? But here the double bond is on the extra methyl carbon. Such kind of conjugation is called cross conjugation. While when it is in one straight line, this is not in one straight line, right? But when the conjugation, which is double bond, single, double, single, is in a straight line, it's called the extended conjugation. And when you have to compare the stability between the two, then extended conjugations are very, very more stable than your cross conjugation compound. Okay? Let us see one example on our screen. Try to answer this question for me. Who can answer this question? Which among the following is more stable compound? Try to answer this. Between the first, I'm labeling it A, B, C and D, right? Between A and B, which is stable? Between C and D, which one is stable? Who can answer this? Again, 30 seconds to answer this on your screen. On your screen, 30 seconds. 30 seconds. Yes, bacha. Yes, bacha. 30 seconds. I'm looking at the chat box. Okay, 2. I have written A, B, C, D. Answer in A, B, C, D. Now, why are you answering 2? Huh? Why are you answering 2? C. Okay. C first answer received by Arav. Arav has said me C and Monisha has told me A. Okay. First again, can you see this is extended conjugation in the A compound? A double bond, single bond, double bond, right? So this is definitely more stable than this because that conjugation is breaking in the middle, right? So this is more stable. Look at the second compound once again. In the second, can you see that this over here, C compound is actually showing your cross conjugation. Cross conjugation. Can you see that this is not coming in a straight line? This is coming as a cross conjugation compound, just like this compound, right? But here, this entire compound is in a straight line. Can everybody see? This entire compound, double, single, double bond is in a straight line. Hence, this is showing your extended conjugation. And I just told you that extended conjugations are more stable. So, the answer is D is more stable in this case and A is more stable in this case. Is this thing clear to everybody? Is this thing clear to everybody? Okay, I'm moving on to the next question. Now you have to compare the bond lengths. Compare the bond length, right? What feature you're going to use in this? The resonating features, just the feature that we just discussed. In resonance, what was happening? The lone pair of electrons, every nitrogen on here has a lone pair of electron, right? And when the resonance happens, the lone pair goes here and the bond gets converted into a double bond, right? And if it's getting converted into a double bond, then its bond length would be affected. Give me the order. Give me the order between 1, 2, 3, 4. Give me the order looking at the screen once again. Looking at the screen once again. Beta, order. You have to tell me the order. Don't have to tell me 1 or 2. Tell me 1, 2, 3, 4. What will be the order? 4, 3, 2, 1. 3, 2, 4, 1. I'm giving you 30 seconds. Very easy question based on the concept that we just did. 30 seconds to answer this. Okay? Nobody is answering me. 4. What is 4, bacha? Tell me the trend. Tell me the trend. 4, 3, 1, 2. First answer I've gotten. Chalo, let us see. Can you see here? Compare the bond lengths. Can you see over here in the first compound? There is no possibility of resonance, right? There is no double bond over here to resonate this lone pair. So first will be the longest bond, right? Because this is a simple single bond. Now let us compare all the other three. All the other three, what is happening? Here, the second is already a double bond, which means it is a full-fledged double bond, which means it is a very, very short bond. Double bonds are shorter. So second will come at the last. I know that. Second will come at the last. I have put it. Now I have to compare 3 and 4. In 3, what will happen? This will definitely go into resonance with this structure, right? And in the 4th, once again, this will definitely go into resonance with this structure, right? Now, bacha, can you see here the resonance is more in the 4th option? When the resonance is more, what it is the case? That this is gaining more double bonded character, right? So it will be 1, 4, then 3, then 2. So this is the correct answer. Did anyone give this answer? 1, 4, 3, 2. Very good. I've already received so many correct answers. So many correct answers. 1, 3, 4, 2 is the correct answer. Actually, it's 1, 4, 3, 2. Correct this, right? 1, 4, 3, 2. We just did it, right? 1, 4, 3, 2 is the correct answer because here extended conjugation is there, and extended conjugation is again a very, very big kind of conjugation. Understood? Now let us move on to the next question over here. Question is from the JEE Main 2021 question. Among the given species, the resonance stabilized carbocations are. Very easy question. We just discussed this. I just told you when the resonance is possible. See, on the same concept, JEE Main question. We just did it. We just did it. Try to answer this question for me. Try to answer this question for me. Try to answer this question for me. Yes, the correct answer is given by everybody. Yes, Ujjwala. Ujjwala, I am going back to the last question. She is asking, ki ma'am, what is... So, can you see here, this is gaining a double bond character, right? This is gaining a double bond character. Now, here, once again, this is also gaining a double bond character. And here, the resonance is even more because these are two double bonds over here. Can you see? So, it is undergoing a extended conjugated structure. Extended conjugated structure, which means the resonating structures have now increased. And I just told you when the resonating structures increase, what should be the case, right? What would be the case? That it would be more stabilized and this will gain a more double bonded character, right? Understood? Okay. First answers I've received is D, C. Okay, I've received so many answers. So among the given species, a resonance stabilized carbocation is asked. Is this resonance stabilized? Yes. Can you see? Here the carbon has a double bonded character, right? And here the positive charge is present, right? So here this is definitely going to show resonance. We just discussed the carbon with a double bond and right next to that carbon should have a positive charge. Will show resonance. Once again over here, this is a double bonded carbon and right next to that carbon has a positive charge. This will also definitely show resonance. We just discussed this topic. Now look at the C. Here is a double bonded carbon and here there is no positive charge. Therefore, this will not show resonance, right? Because this carbon should have had the positive charge in order for it to show the resonance, but this carbon does not have it. So this will not show resonance. Now the D option. D here once again. The double bonded carbon itself has a positive charge. So this again does not show resonance. In which case, the double bonded carbon right next to that carbon should have a positive charge. Only in such cases resonance is observed. So the correct answer is C. Whoever answered C is extremely right. Whoever answered C is extremely right. Okay? Correct. Now let us move on to the next question. Next effect is mesomeric effect. This is once again a variety of your resonance only, right? So whenever the resonance is conjugating like this in the chain or in the ring, what is happening? For example, in your ring, what is happening in this chain? The oxygen is there. Oxygen has lone pair of electrons and it is donating the lone pair of electrons for resonance, right? So what is happening in this structure? That it is increasing the electron density towards the chain or the ring. So such effect is called either resonance effect or mesomeric effect, which we just discussed. It is the same thing. Mesomeric and resonance are the name of the same effects, right? So plus R is when the electron rich species will give electrons to the alkyl chain. Okay? This is called plus R effect. These are some of the groups which show plus R effect. What should be the criteria? That they should have lone pair of electrons, isn't it? For example, the oxygen over here has lone pair of electrons. Here once again lone pair, lone pair, lone pair. So all these species with lone pair of electrons will definitely show plus R effect, which is increasing electron density in the ring or in the chain, right? Okay? For example, what is the order of plus M effect now? Given over here. Once again, here carbon with a negative charge will give the electrons easily as we just discussed. Then the nitrogen, then the oxygen. Why? Because oxygen is more electronegative. Hence, it will hold the electrons closer to itself. It will not readily donate the electrons, but carbon will readily donate the electrons. Similarly, between NH and NH2, what is happening? NH will definitely easily give away the electrons. Then you are comparing your NR2, NHR, NH2. So what is happening? As the alkyl groups are increasing to the nitrogen. Can you see it here? It is NR2, which means two alkyl groups are attached to nitrogen. And we know alkyl groups show plus I effect, which is electron donating effect. So these will definitely be higher donating power than with just one alkyl group with the NHR, then NH2, then it is followed by the NHC double bond OR. So always remember one other thing. Whenever there is a compound or an atom with a multiple bond here, so all these multiple bonds have just one thing to do, which is these are electron withdrawing groups. Understand this thing. Always remember, whenever a multiple bond is there, just keep it in your head, that will be an electron withdrawing group. Hence, the electrons on these nitrogens will be withdrawn by the carbonyl group over here. Hence, the availability of these lone pair to donate is less. So, hence this trend is followed. Now, here to this nitrogen, you have attached two electron withdrawing groups. Hence, this nitrogen's lone pair ability to donate is even lesser. Understood this? Similarly, some more trends are given, but you understood the concept, right? So the atoms which have the more electron donating capacity will show more plus R or plus M effect. Understood? So these are effectively doing what? These are effectively increasing electron density. Electron density in the ring or in the chain, wherever they're attached. They're giving electrons to the ring or the chain. Okay? Now let's talk about the minus R or minus M effect. In this is once again a form of resonance only. Here what happens? An electron withdrawing group, like any group with a multiple bond in it, as I just told you. Here nitro is a multiple bonded group. So all these groups will show minus R or minus M effect, which means these are all electron withdrawing groups. These are withdrawing electrons from the chain or the ring that they're attached to. They're just decreasing the electron density. Now let us look at what is the trend. For example, nitro groups, the aldehyde, ketone, nitriles, acidic and sulfonyls. Can you see in all these examples there is a multiple bond present? Can everybody see that? And I just told you this is one of the identity of electron withdrawing groups. So these are all electron withdrawing groups and they show minus M effect or minus R effect. And this is the order followed. The order is nitro shows the highest withdrawing power, then followed by the nitrile. Very, very important order. Bookmark this, right? Take a screenshot of it. Then followed by the aldehyde, followed by the keto, followed by the ester, followed by the amide group. Very, very important trend. Understood? I am moving on to the next effect, which is hyperconjugation. Again, a very important effect. Every year, questions are asked from hyperconjugation. What you have to remember in hyperconjugation, I'm just going to tell you that. You don't have to go into much details. You have to remember that whenever, can everybody see over here? Whenever there is a sp2 carbon, can you see this is a multiple bonded carbon, double bonded carbon. So sp2 bonded carbon, right next to that carbon, there should be another carbon. And how many hydrogens are present on this carbon will determine the hyperconjugating effect. So what did I tell you? Right next to the sp2 hybridized carbon, there should be a carbon which should have hydrogens attached to it, right? More the number of hydrogens, more will be the hyperconjugating structures and more stable will be the compound. Understood this? More the number of these alpha hydrogens, these are called alpha hydrogens, and more will be the number of stables, more the number of alpha hydrogens, more stable will be the compound as it is written over here. For example, I will tell you one more thing. Order based of the electron releasing effect. So we just discussed the inductive effect also. In inductive effect, I told you that tertiary carbonide, the tertiary alkyl has more power of electron donation than your secondary, then your primary, and then your methyl group, right? This is the electron releasing density, isn't it? This is the electron donating group density. But if we talk the same on the basis of hyperconjugating structure, then what is happening? Your methyl, your alpha carbon, if it has 3 hydrogens attached to it, it will be what? It will be what? More hyperconjugating structures it will show. It will be a much more stable compound. Similarly, here this on the alpha carbon there is just 2 hydrogens. Here on the alpha carbon there is just 1 hydrogen. Here on the alpha carbon there is again 3 hydrogens. Okay, no, this is not the alpha carbon, this is the alpha carbon, and here there are 0 hydrogens present, right? So as the number of hydrogens are increasing, what is happening? The hyperconjugating structures are increasing, and so is the stability. So both of these things, that is the plus I effect and the hyperconjugating effects, are actually polar opposite. So ma'am, how will we determine the stability when we are talking about stability order? I will teach you with examples. Without examples, you won't know, but you should know the basics of what is hyperconjugation, right? You understood the basics now? Okay? Now, this is what we're going to discuss, that the stability of alkenes. As I told you, whenever an alkene is given to you, the carbon next to it, how many number of hydrogens that carbon have, that alkene will be more stable. More number of alpha hydrogens, more stable is the compound. Okay, and also we're going to discuss the acidic character based on hyperconjugation and also the stability of carbocations. So one by one we're going to see everything. First of all, let us look at the stability of carbocation based on the hyperconjugating structure. First, let me know what is the hybridization of a carbocation. What is the hybridization of a carbocation? Can anybody tell me? Is it sp, sp2 or sp3? What is the hybridization of a carbocation? Yes, what? Beta, just study hard, M. What else can I tell you? M is saying, ki ma'am, I only got 10 percentile in my first attempt. But you have to study hard, you have to just go through the basics, because this year the paper was very basics, right? If your basics are not okay, if they're not very strong, then it's very hard to score marks, I know. Okay? But don't worry, sp3, who is saying sp3? The hybridization of carbocation is bacha sp2. Always understand this. It is sp2 hybridized carbon, right? And I just told you in hyperconjugating structure what happens? The carbon next to the sp2 hybridized carbon, we count the number of hydrogens attached to it, and more the number of hydrogens on this alpha carbon, more stable will be the compound. Same thing you have to do in this, right? All the carbocations are present. Carbocations are sp2 hybridized. Right, now let us count the number of hydrogens. In the number 1, how many hydrogens are there? 1 hydrogen and 2 hydrogens. So this has just 2 alpha hydrogens, isn't it? Now count the number of hydrogens in second compound. This has 1, 2, 3, 1, 2, 3. Isn't it 3? Which means second has 6 alpha hydrogens. Similarly, the third over here, how many alpha hydrogens are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this has 9 alpha hydrogens. Similarly, in the fourth, how many alpha hydrogens are there? 1 and 2. Just 2 alpha hydrogens once again. Right? Now here once again, what can you see? How many alpha hydrogen? 1, 2, 3, 4. Isn't it? So this once again has 4 alpha hydrogens. Is this thing clear to everyone? Okay? Now tell me, what do you think should be the answer? What is the trend now? So I know that third, ma'am, is the most stable. Third is the most stable because it has 9 alpha hydrogens. Then followed by the second, right? It has 6 alpha hydrogens. Then followed by the fifth, it has 4 alpha hydrogens, right? Now between 1 and 2, which do you think is the most stable? 1 and 2. Which do you think is the most stable? Between 1 and 2. So these are with equal stability, isn't it? These are with equal stability. I can write that 1 and 4 are with equal stability. Is this thing clear to everyone? Is this thing clear to everyone? Yes. Okay? 3, 2, 5, 4, 1. Who is writing? Okay? Shall we move on to the next? Okay. Okay. The next is your comparison of all the effects. We just studied all the effects. We studied, first of all, we studied aromaticity. Then we studied inductive effect. Try to recall all the effects. Then we studied resonance effect. Then we studied your hyperconjugation effect, isn't it? So we have studied all these effects. Now let us compare between these things. So in inductive effect, bacha, what was happening? Only sigma-sigma interaction was happening. Understand that. There was no involvement of pi bonds or pi electrons. But in resonance, what was happening? Pi-pi interaction was happening, right? A double bond and a lone pair of electrons, a double bond and a negative charge. So a pi-pi interaction happens in resonance. But in hyperconjugation, a sigma-pi interaction happens, right? Because why? The sp2 hybridized carbon as well as the sp3 hybridized carbon, that interaction was happening, right? Understood these things? Now if you have to talk about the stability, then understand bacha ki aromatic compounds are the most stable, or they are also given the most important. So whenever we are trying to calculate the effects, aromatic compounds will come on the top, then the resonance, then we will see for the resonance structures, then we will see for the hyperconjugated structures, and then we will see the inductive effect. Ma'am, what do you mean by that? What is this trend is even trying to tell you? First of all, keep this trend in mind. The trend is aromatic, resonance, then followed by hyperconjugation, then inductive effect. Understood? Now, how to use this? I will teach you in questions. Only when you do questions, you will understand. You just have to keep this order in mind. Okay? Kept in mind. Now, let's do some questions. Let's do the acidity order questions, right? Very important. Every year, acidity, basicity, stability orders are asked in your exams. The correct order of acidic character of the following compound is, who can answer this question for me? The correct order of the, yes, the correct order. Try to answer this question for me, then I will tell you the answer. Acidic, once again I will tell you the compound which easily gives away the H plus, right? The compound which easily gives away H plus will be the more acidic compound, isn't it? Those will be the more acidic compound. Now what will the H plus giving away depend upon the stability of the anion form, isn't it? Now, for example, if I take away H plus from here, the anion formed is this. 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 Understood? After taking away the H plus, these kind of anions are formed. Now, look for the stability of these anions. Now, tell me the answer. Now, tell me the answer. C, B, C. Okay, so many answers I have gotten. B, B, C. Okay, people. Okay, I have also gotten A as the answer. Mostly people are saying either C or B. Okay, and somebody has said 1. Okay, let us see. So, all of these are first of all acid and phenol group. So, first of all, keep it in mind. All these 3 are acids. So, obviously, acid compound, carboxylic acid compounds will be more acidic than the phenol compound. That is so in mind. Okay, so between these acids, let's compare first. Okay, so these acids, can you see NO2 is a electron withdrawing group, isn't it? This is a electron withdrawing group. Hence, this is stabilizing the negative charge. I'm already negative and you're taking away electrons from me. Hence, you're making me stable, right? What is a stable species? A neutral species. If I have a too much negative charge, I want to get rid of that negative charge, and this NO2 is doing just the same, right? So second will be the most acidic, right? Now next comes your third, right? Third. Now what will come? CH3 over here. Can you see CH3 over here, bacha? CH3 is actually electron donating group to the COH group. So what it is doing, it is decreasing the acidity over here. So next will come what? Second, third, and then it will come what? Second, third, and then bacha, it will be your fourth, and then it will be your first. Why fourth will come? Because somehow it is an acid, and carboxylic acids will obviously more acidic than a phenol group. Understood? Understood? So this will be the order followed. Correct answer is B. Whoever gave me B as the answer is absolutely right. ठीक है? Understood? ठीक है? Very good. Chalo. Next is this very beautiful question once again. What is the correct order of acidity of the protons marked A to D in the given compounds? What is the correct order of acidity? Who can answer this question for me? You have to tell me which protons are easy to donate. Once again, it's a very beautiful question. This is also your JEE question only. This is I as a JEE question. This is a JEE advanced question. Where was this asked? I think this is a JEE advanced question. Try to answer this question for me. Okay, also remember, bacha, one thing, ki whichever questions are asked in your JEE advanced, right? Those same questions next year will be asked in your JEE Mains. So don't forget, if you're doing PYQs right now, don't forget to even do JEE Advanced PYQs, because same questions or similar concept questions will be repeated in JEE Mains so many times this trend has been seen. So you cannot skip even JEE Advanced questions. Okay? Now let us try to solve this over here. So can you see there are 1, 2, 3, 4 protons given over here. The first proton that I'm seeing is attached to the COO group, right? So here when I take away this H plus from here, this is an acidic group. Once again, as I told you, acidic group will obviously, because this is an acidic group, carboxyl group, easily gives away H plus. So this will definitely be the most acidic proton. So HC will be the most acidic. Okay? Followed by, can you see over here, this HD. HD is right next to the COO group. I'm drawing this over here. Can I draw this over here? I'm drawing this structure like this. This is your benzene ring here. This is your this structure. This is your C double bond O, O. Here is the HC proton. Here is the HD proton, right? Here is the, okay, 1, 2, and 3, and HA. Okay. And, what did I do? Yes, HA is here. Sorry. Just consider that HA and here is the triple bond, right? This is the structure given to you and here is the HB given to you. Correct? Now, as I told you, HC is the easiest to go away because it is connected to the carboxyl group. So, this is the most acidic proton. Now, look at the HD over here. To which carbon is it connected? Right next to it is an electron withdrawing group, right? So, as soon as I take out HD, what will be left behind? A negative charge on this carbon. And this negative charge is stabilized by the electron withdrawing group over here. So, HD will be the most acidic after that. Now, between HB and HA, can you see this HA over here? This HA is connected to the sp hybridized carbon, isn't it? So, when this HA leaves, the negative charge will be on the sp hybridized carbon. As I told you, sp hybridized carbons are actually more electronegative, right? These are very electronegative atoms and the negative charge is always stable on electronegative atom. So then it will be your HA followed by then your HB. So this is the acidic trend. Is this thing clear to everybody? HC, HD, HA and HB. Right? Right? Understood everybody? Understood. I'm moving on to the next question. The most stable carbocation for the following is, try to answer. This is again based on your resonance. Can everybody see? Very basic resonance. Very, very basic. If you can answer this question, it means your basics are very fine. This is once again your JEE Main 2023 question. See, such basics questions are asked. Sir, basic. The most stable carbocation where the positive charge would be more stable. Who can answer this? I'm looking at the chat box once again. I will not answer this. You will answer this for me. I'm looking at the chat box. Yes. Try to answer this 30 seconds. In 30 seconds, you have to answer this. Try to answer this question for me. B. Arav has given me B. Sai Harini B. Okay. So, I've received the answer. Nikhil B. Okay. Very good. Everybody is giving me the same answer. B. Why do you think B is the answer? B is not the answer, bacha. Look at the resonating structures. Look at the resonating structures. Once again, where do you think the most resonance is possible? Here, once again, bacha, if the lone pair of atom are present on this atom, then the double bond should have been on this atom, right? Then only this could show a very good resonating structure. B cannot be the answer. For B to be the answer, what should have been the case? For example, here, look at the D option. Here it will definitely show resonance. This is definitely showing resonance. But here, once again, the positive charge is very far away. But look at the C option. The nitrogen's lone pair will go over here This will get converted into a double bond. This double bond goes over here. Then this double bond goes over here. So can you see, from starting from this nitrogen till this positive charge, there is a constant resonance going on, right? So this will definitely be the more stable carbocation, which will be the C, because there is a constant stable resonating structure going on. Is this thing clear to everybody? Is this thing clear? But this resonance is breaking in D, right? Here the positive charge is very far away from this double bond. This resonance is breaking in D, cannot be the structure. This resonance is not possible in A, because for resonance to take place, the double bond should have been here, but it is not. Similarly, here also no resonance will take place because the double bond is far away. So the correct answer is C. Only in this case there is a continuous resonance possible. So you have to look for resonating structures. That will be the most stable carbocation, right? Now let's move on to the next question. Understood that question, everybody? Everybody? Okay, very good. Correct order of basicity of various nitrogen. You have to answer the correct order of basic nature, basicity. What do you think would be the correct order of basicity? Basicity, again I'm going to tell you, nitrogen has lone pair of electrons. So whichever can easily donate electrons will be most basic, right? Most basic compound. That is the only thing you have to look for. First nitrogen's lone pair of electrons are over here. Second nitrogen's lone pair of electrons are here. And third nitrogen's lone pair of electrons are here. Okay? Now let us see nitrogen third. Let's start from here only. Can you see there is an electron withdrawing group attached right next to it? So the availability of these electrons will become less, because what will happen? These will participate in resonance, and hence these electron pairs of nitrogen are not available. Not available, isn't it? Because it is right next to the double bonded structure. But look at the second number of nitrogen. Here, one alkyl group, second alkyl group, third alkyl group. So all these alkyl groups are what? Plus I groups, which means these are increasing electron density of nitrogen. This alkyl chain. Hence, these lone pair of electrons are very easily available to donate, because all electron donating groups are attached to it, right? So I think second should be the number one case. Now let us look at first also. In first, what is happening? You can argue, ma'am, here a electron donating group is attached. But can you see here, this nitrogen is again can take part in resonance with this sp2 hybridized carbon, isn't it? So this is becoming a little bit less. So the electron donating capacity is most of second, then of first, and then of your third. Okay? So the correct answer is B. Whoever answered B is yes, whoever answered B is right. Whoever answered B is right. Okay? Understood this thing? Understood this thing? B is the correct answer. Let's move on to the next question. Next is, because we were discussing about basicity, the next thing you should know is the basicity of amines. Again, a very important concept asked every time in your exams. So amines, whenever there is an alkyl amine, alkyl means this R is an alkyl group, then that is a very basic compound. But what happens with aniline? In aniline, can you see? Aniline, what happens? These electrons participate in resonance. Hence, the availability of these electrons are very less to donate. So, therefore, amines are more basic than anilines, right? Amines are more basic. Why? Because in amines, what is happening? NH2. This is the group. Here, nitrogens are very, very available to donate. While in anilines, the lone pair is actually participating in resonance. So when it's participating in resonance, it is not available to donate. Hence, it is becoming less. Understood this thing? Now let's move on to the next. So these are some of the resonating structures due to which the basicity of aniline is reduced. See, can you see? Due to this, the basicity of aniline is reduced. Now, what is the aniline basicity in aqueous medium, right? So whenever the question is asked in aqueous medium, again, every year this question is asked, right? In aqueous medium, the basicity of anilines, of amines actually depend on various factors, 4 factors: solvation, hydration, the steric hindrance effect. They depend on so many factors, and hence the order of basicity is actually a little bit different, right? In aqueous medium, right? In aqueous medium, so for example, let me make you understand the amine. Amine, for example, this is the ammonia molecule, right? So as soon as I change the hydrogen, replace the hydrogen with R group, for example, here I made it NH2R. So this became the primary amine. For example, I made it the NHRR group. So this becomes the secondary aniline. Now, secondary amine. Now, if I replace all the 3 hydrogens with R group like this, this became the tertiary amine. Now, can you see what is happening? This R is actually a electron donating group, isn't it? This R is actually a plus I group, a electron donating group on the nitrogen. So what is happening? It is increasing the basic character of the amine. But this bacha only happens. This is the order of basicity. Basicity order in gaseous medium. What is happening? Tertiary amines will be the most basic because the more R group, which means more plus I effect, more electron donating effect. So more donation capacity of this nitrogen lone pair, right? But this is only true in the gaseous phase. What happens in the aqueous phase, bacha? Aqueous phase, if the ethyl groups are present with the amine group, then secondary amines are the most basic, followed by tertiary amines, followed by primary amines, and followed by ammonia. And what happens in case of when the R group is methyl group, then once again secondary amines are more basic, but here the trend changes. Then comes the primary amine, then the tertiary amine, and then the normal amine. Understood? So this is the basicity trend of amines. Amines follow a very haphazard trend due to a lot of factors: hydrogen bonding, solvation, hydration, steric hindrance. Due to that, the order changes in the aqueous medium. In gaseous medium, it is what you expect. More the number of alkyl groups, more will be the basicity of that compound. Understood? ठीक है? Chalo. Next is this bacha. Which of the following options is the correct order of relative stabilities of cations as written below? Tell me the stability of anion. Who can answer this question for me? Try to answer this question for me. What do you think should be the stability of the carbocation? Yes. Monisha is asking, ma'am, why primary is more basic than tertiary? Then Monisha, that answer will actually come when you read the amines chapter, right? In amines chapter, that thing is given that the basicity of amines in the water, in aqueous medium, depends on a lot of factors. Like the steric hindrance, if there are too many groups around it, then it is too sterically hindered to form hydrogen bonds with water, right? So hence its basicity decreases. All these, that's why I'm telling you right now, those are the factors on which basicity of amines depends, okay? Which we read in the amines chapter. Right now, I'm just telling you the trends which you should know when you're solving the questions, right? We're not going into much detail because then there is so much to discuss, na? Hai na? Because this depend upon 4 factors. You can go check out your amines chapter, or you can check out my video on amines where I've explained it in very much detail. Okay? Try to answer this question for me. Which of the following options is the correct order of relative stability of cations? Okay? Can you see? This is a carbocation over here. What kind of carbocation this is? This is a benzylic carbocation. Benzylic carbocations are very stable. Why? Because these can undergo resonance. Okay? Again, a stable species. Here, bacha, what is happening? What kind of carbocation is this? What kind of carbocation is this? Can you see that if now so many effects will take into place. What effect will take into place? Can you see, bacha, that here there are 0 alpha hydrogens present? If I talk about your hyperconjugative effect, here the inductive effect will not work. I'm talking about the hyperconjugative effect. Now the carbon next to this positive carbon, right? This is the sp2 hybridized carbon, and the carbon next to it is called the alpha carbon, and that alpha carbon should have hydrogens on it. But here this alpha carbon has no hydrogen, 0 hydrogen, so this will definitely have the least stability carbon of carbocation. Now look at this carbocation over here. How many alpha hydrogens does it have? It has 4 alpha hydrogens. Can everybody see that? It has 4 alpha hydrogens. So if we are counting alpha hydrogens in every case, so we can count alpha hydrogens over here. 1, 2, 3, and this is 1 alpha hydrogen. This actually has 1 alpha hydrogen, isn't it? So now what should be the stability order? Now you answer this question for me. You answer this question for me. What is the stability order of this? 1, 2, 3. 1, 2, 3, somebody is writing, which is extremely wrong answer. Extremely wrong answer. Yes, bacha, what should be the stability order? What should be the stability order? No, bacha, it's not 1, 2, 3. Can you see? Can you see that second has the highest number of alpha hydrogens? Isn't it? Highest number of alpha hydrogens. So second should have the highest. Then should be, that's a benzylic carbocation. 1, 2, 3. Correct. That's a benzylic. That's extremely stable. Followed by the second, followed by the third. Yes. ठीक है? Benzylic. That's a benzylic. Okay. Next is over here. Now I'm going to teach you about some of the properties of these carbocations. Once again, bacha, what actually happens with carbocations. So this thing is such kind of questions are becoming very popular now. What questions? Can you see this structure on your screen? Can you see this? This is called tricyclopropyl cyclopropenium cation. Okay? Just remember the structure in your head, because this question has been asked like 3 times in your JEE. 2 times in mains, 2 times in advanced and 1 time in mains. So I'm guessing that this is going to become a more popular set of questions now. So I have to let you know the entire stability order of the carbocations that is followed. So the most stable carbocation in the entire world, the most stable carbocation is this. This is the most stable carbocation. Okay? Here the carbon over here has a cyclopropane ring. Again attached by cyclopropane, attached by cyclopropane, attached by cyclopropane. This kind of structure, if you see in an exam, would be the most stable carbocation, followed by the tertiary carbocation with the 3 cyclopropyl rings, followed by the secondary, followed by the primary, right? So this is the carbocation stability order when you see such a cyclopropyl species. Now I'm going to answer another thing for you. Now the most stable species I just told you are the aromatic species. So if any carbocation, bacha, is an aromatic carbocation, will definitely be the most stable carbocation. First, aromatic. Next come this. Next come this species. Next come are all these tricyclo. So I'm just writing tricyclo species, right? Which will follow this order. So aromatic carbocations, number first stability, followed by the tricyclo stability, which I just told you. After that will come the benzylic carbocation, which benzylic carbocation, followed by the allylic carbocations, right? Followed by what? Then followed by your tertiary, secondary and primary carbocations. Understood? Followed by your vinylic carbocation, followed by your phenyl carbocation. Understood? What is phenyl carbocation? When the positive charge is directly on the benzene ring. That is the phenyl carbocation. Understood? So please understand difference between benzylic, allylic, phenyl. So please write down this order. What are the most stable carbocations? Which are the aromatic carbocations, followed by this species. Then will come your benzylic carbocations. Then comes your allylic, tertiary, secondary, primary, vinylic and phenyl carbocation. Is this thing clear to everybody? Is this thing clear to everybody? Okay, bacha, understood. Now moving on to the next thing. Try to answer this question for me. The 3 carbon anions follows which order of stability? Who can answer this question for me? The 3 carbon anions follows which order of stability? Now you have to tell me the stability order of carbon anions. Understand? I already have a negative charge on me. How will I become more stable? When somebody will take away the negative charge from me, right? Then I will become stable. So that's the only funda that you have to use. Try to look at these groups attached over here. So nitro is attached on the ortho, meta and para position, right? Try to answer this question for me. What do you think is the answer? What do you think is the answer? No, bacha, phenyl is the most unstable. Phenyl is the most unstable. Phenyl is the least stable, bacha. SV, phenyl. Vinyl and then phenyl is the least stable, right? ठीक है? ठीक है? Yes, DA. Okay, bacha. Here NO2 is showing what all effects? NO2 is showing minus I as well as minus R effect, isn't it? Here NO2 is showing just minus I effect. Here NO2 is showing minus I as well as minus R effect. Understood these things? Now, bacha, as you know, inductive effect is distance dependent, which means as the distance is increasing, inductive effect will decrease. So first we'll have the highest minus I effect. So the answer is first, third and second. So the correct answer is B, right? First and third are showing 2 types of electron withdrawing effects, which is minus I and minus R. Both are electron withdrawing effects, right? But here what is happening? The I effect is more. Why? Because it is near that negative charge and I is always distance dependent. The correct answer is 1, 3, 2, right? Understood this? Understood this, everybody? Chalo, I'm moving on to the next. Now the effect of substituents we're going to see. Effect of substituents means what? I already explained it to you. This is the benzene ring, right? On the benzene ring, there are 2 types of groups can be attached. One is that group which is the electron donating group, isn't it? Electron donating group. Those are called activators. What are they called? Activators. One which is increasing the electron density in the ring are called activators. What are those groups? Those groups are anything which has a lone pair of electrons like OH, NH, COCH3, NH2, OCH3, anything, as well as the alkyl groups, as well as even your phenyl or benzyl ring. These are all your activators, increase the electron density in the ring, and all of them are bacha your ortho and para directors. Meaning what? If any of these groups are present on the ring, if any of these groups are attached on the ring, then the next incoming electrophile will attack either on the ortho or on the para position. Understood? Either on the ortho or the para position if these groups are present. Now on the benzene ring, there is another possibility. On the benzene ring, you have electron withdrawing group. Electron withdrawing group, which means any group which has a multiple bond in it. So whatever happens with the electron withdrawing groups, these are called deactivators, which means what? These are deactivating ring, which means taking away electrons from it, right? These are called deactivators. Understand these terms. Now, bacha, what is happening? These electron withdrawing groups are always meta-directing groups. What? Meta-directing groups. Okay, but there is one exception. One exception is your halogen. Your halogens are actually deactivators, which means they decrease the electron density in the ring, but they are ortho and para directing groups. Understood? So whatever were the activating, which are increasing the electron density in the ring, were actually ortho para directing, and which are decreasing the electron density in the ring are meta directing, except your halogens. which are decreasing electron density in the ring. They are deactivators, but they show ortho and para-directing effects. Understood this thing? Shall I move forward now? Shall I move forward to the next topic, which is your isomerism? Again, very, very important topic. So, there are various kind of isomers. First of all, constitutional, stereoisomers, and conformational. All of these three are very important from a JEE perspective. What are constitutional isomers? Once again, but in constitutional isomers, these are what? They have the same chemical formula, but their bonding is different, right? In stereoisomers, what happens? Their chemical formula is same, their bonding is same, but the arrangement in space is different. In conformational isomers, which are what happens? The isomers have the same connectivity and they can interconvert into each other. I will explain it to you with examples and you will understand it better, right? And stereoisomers are again of two types, enantiomers and diastereomers. Enantiomers are basically mirror images of each other, right? Diastereomers are what? Which are not mirror images of each other. We will see with examples, then you will understand better. Right now, just keep it in your head. Three kinds of isomerism. Stereoisomers have enantiomers and diastereomers. Okay, let us see structural isomers, which is constitutional isomers once again. Chain, number first is chain isomerism. In chain isomerism, what happens? The position of the alkyl groups keeps on changing. For example, let us look at C4H chain. It can be written as a normal butane or as a branched chain, right? So whenever we are writing a branched chain, this is called chain isomerism. Similarly, C4H chain can be written as an alkene, right? Now, please pay attention to this alkene. Here, the position of alkene is number 1. And when I am creating a chain isomer of it, when I am moving a methyl molecule, the position of the alkene is still on carbon number 1. Okay? The position of double bond has not changed. Only the position of the methyl group has changed. Hence, this is a chain isomers, right? Position of double bond, position of functional groups do not change in chain isomers, right? Now, let's look at position isomers. Position isomers are what? For example, let us look at this propanol compound. 1-propanol, the OH is on the number 1 carbon, but here the OH is on number 2 carbon, right? The chemical formula is same. What is happening? The position of the functional group changes. Hence, this is a position isomer. Similarly, look at this double bond over here. In the first example, the double bond is on first position. In the second, the double bond goes on to the second position. Hence, the position of double bond, the functional group is changing. Therefore, this is position isomerism. Very important example. Only enough to understand these isomerism. You do not need any more reading beyond these examples. That is my guarantee. You do not need any more reading. Okay? Next is functional isomerism. Functional is what, bacha? When your, for example, this compound C2H6O can be written as two kind of functional groups. Number first kind is your ethanol functional group. Number second kind is your ether functional group. So can you see ethanol and your ether both are actually functional isomer. What is happening? The molecular formula is same. I'm just writing these two kind of isomers into two different kind of functional groups, right? So alcohols and ethers are functional isomers. Similarly, aldehydes and ketones are once again functional isomers. Similarly, your acids and your esters are once again your functional isomers. So what is happening? Molecular formula is same, but you're changing the functional group. Hence, functional isomers. Okay, easy peasy. I'm moving on to the next thing, which is the ring chain isomers. This is shown by a alkene and a cyclo group, cyclo ring group, right? Alkene and a cyclopropane shows what, bacha? A ring structure. Cyclopropane structure, cycloalkane structure actually shows ring chain isomerism. Both the alkene and the cycloalkanes have same molecular formula. Can you see here the alkene formula is C3H3 and 6. C3H6, here also the formula is C3H6, right? So they have the same molecular formula, just that these are ring chain isomers of each other. Similarly, metamerism, again a very important example. Metamers are what? Please don't be scared. Very easy. Metamers are, for example, this is an ether given to you, right? Can everybody see? This is an ethoxyethane, which is the example of ether molecule. See, around the oxygen, both the alkyl groups are ethyl groups. Now what do? I keep the functional group same. Now the functional group is ether only. But now what I've done? Here I've done methyl group. I've attached methyl. Here I've attached propyl group. So I've just moved the position of alkyl groups. Similarly, I can also write it as 2-methoxypropane. So what am I doing? I'm changing the position of the alkyl groups around the functional group. And what I'm getting in return is a metamer, right? Here I'm changing nothing, just the position of your alkyl groups around the functional group. So this can happen in two cases. One is the ether that we just discussed. In ether, the alkyl chains can vary. Okay, similarly, this can happen in amines. Okay? For example, the secondary amine, tertiary amine can be interchanged into each other. Okay? It can also happen in ketones. Yes, it can also happen in ketones and esters also. So these are some of the functional group which shows metamerism. In metamerism, what is happening? For example, if the keto group is over here, I will explain to you with another example, right? And here is the CH3 group and here is the C2H5 group. This is the one form to write this structure. The another form could be that I write CH3, CH2 over here and C double bond over here and CH3 over here, isn't it? So this is another form to write. So I can keep on changing the alkyl groups around the functional group. That is called the metamer. Is this thing clear to everybody? That is called the metamer. Next is tautomerism. Again, a very important kind. First important kind of tautomer that is in your subject is the keto-enol tautomer. What is that? For example, whenever a double bond, alkene, is present and on the same carbon, on the double bonded carbon, there is a presence of the OH group. Okay? This is called ene because of the double bond, ol because of the alcohol group. This is the enol form. Now here what can happen? This lone pair of electrons can go over here and this can go over here, this double bond electrons, right? Now what is forming? This gets converted into the keto form because the lone pair gets converted into a double bond and forms a keto group, and the negative charge goes on this carbon and this H positive that came out of here gets attached over here and you get a keto form. So this is keto-enol tautomerism, nothing. It is another form of resonance only. As you can see, I'm doing nothing. I'm making a resonating structure, right? So this is another form of resonance, but because this is between two functional groups, alcohol and ketone, hence it has got a different name to it called keto-enol tautomerism. Easy. Now answer this question for me. Which of the following pairs of isomers is an example of metamerism? Who can answer this? You have to tell me which of these are metamers. I just discussed what are metamers, right? Try to answer this question for me. I'm looking at the chat box. Only 30 seconds are enough to answer this question. 30 seconds. Yes. 30 seconds. People are saying I'm looking sleepy. Am I looking sleepy? Probably because it's like 11 p.m., right? Probably because it's 11 p.m. and I'm in the office since the early morning. Okay, D option, very good. Whoever answered D, I'm very proud of you, Manisha. Wow. Very good, Soumya. Very good, Manisha. Very good, Lakshmi, Lata. Very, very good, SV. Very good, Ashwarya. Very good. Very, very good. Yes, the answer is D. Can you see? The ketone group here is moving here and there, right? The alkyl groups I'm keeping on changing. So hence this will definitely show metamerism. What were the metamers once again? Around the functional group, the number of alkyl chains keep on moving. That was the metamer. So D is the correct answer. Very, very good. D is the correct answer. Now answer this question for me. compound with molecular formula C3H6O can show which kind of isomer? Who can tell me this? Who can tell me the answer to this question? Compound with the molecular formula C3H6O shows what kind of isomerism? Beta, this is an English channel, so I cannot tell in Hindi. I'm really sorry about that. So first answer I've gotten by Mohammed is B, Mini is saying D, Daniel is saying D. Beta, this is an English channel. Beta, there's a Hindi channel for JEE as well with the name Vedantu JEE. You can go check the videos out on that channel. They teach in Hindi, right? We teach in English. Okay, I've received various answers over here. So C3H6O can be written as what? Can I give you as homework, guys? C3H6O. Once again, what do you think? What do you think should be the answer? So the correct answer here is C3H6O can be written either as an aldehyde or as a ketone molecule, right? So because I'm converting two kinds of isomers, two kinds of functional groups, hence this is showing functional group isomerism. So whoever answered D is correct. I can write it either as an aldehyde or as a keto group, right? Understood that? Shall I move on to the next question? The next question on your screen, this I'm giving you definitely as homework. I'm not answering this question right now. See, what is the purpose of me showing you these kind of questions? That such questions are asked in your JEE exam. This is JEE 2023 question. Last year was asked based on just isomerism. So do not forget to skip isomerism, as I've already taught you. That's the only thing you need to know. And if you learned that right now, which I taught you in the last 15 minutes, you can definitely answer this question. Again, a very easy question. Easy questions are asked. Okay? I'm moving on to the next question because this is very easy to just answer. Now we're moving on to the stereo part of the isomerism. Stereoisomerism. Number first is the geometrical isomerism. What are geometrical isomers? Those are the cis-trans isomer. What you have to remember, it's just that cis-trans, EZ, whatever you call. So around it generally happen around a double bond, right? There should be the presence of a double bond, and around the double bond if the same atoms are at the same position, then it is a cis isomer. But if the similar atoms are opposite to each other, it is called a trans isomer. Simple. So this is what is happening. Can you see? To this carbon only, to this carbon, the groups are not changing, right? But the position of that groups are changing. So here what is happening? That the arrangement of position in space is changing in stereoisomers, but the connectivity remains the same. Understood? Now, how to predict the number of geometrical isomers? So this is a very good funda. Okay, take a screenshot of this because questions like this have been asked in your JEE 2024 as well, 2023 as well. Very important questions, and sometimes numerical based questions are asked on this. So how will you predict which compound has how many isomers? So what you will see, first of all, you will detect the number of double bonds. For example, this is the compound given to you. 2 double bonds are there. Okay? Now around those 2 double bonds. So 2 double bonds is a even number, right? 2 double bonds is a even number, isn't it? Now, bacha, in that case, what you have to do? Here you have to see how many groups are attached. Like this. Okay? Like this, the groups will be attached. And if these groups are similar to these groups, this, for example, if there is some symmetry is present, so number of geometrical isomers in case of symmetrical alkene, this is a symmetrical alkene, is same things are present, then the number of geometrical isomers will be 2 to the power n, right? 2 to the power n. But number of geometrical isomers in case of unsymmetrical alkenes, it will be 2 to the power n minus 1 plus 2 to the power p minus 1, where n, if the n is even, n is what, bacha? N is the number of double bonds. If n is even, then p ki value would be n by 2. If n is odd, then p की value will be n plus 1. I know it is a bit tricky. You might not be understanding, but this is the formula, right? This is just to make your life easy. So what you have to do, count the number of bonds. If the number of bonds is even, right? Now, first of all, just look if it's a symmetrical alkene. If it's a symmetrical alkene, simple, 2 to the power n. N is the number of double bonds. Double bonds, for example, 2 double bonds are there. Okay? But if it is unsymmetrical alkene, then it will be problematic. Then you have to use this entire big formula. But in your exams, I'm again telling you, majority of the time, symmetrical alkenes are given and you just have to apply 2 to the power n. N is the number of double bonds. That is it. Understood? Understood. So this is just to make your life easy. Now answer this question for me. Which of the following compounds show geometrical isomerism? Who can answer this question for me? Who can answer this question for me? "30 seconds to answer this question. 30 seconds to answer this question. Also, let me know in the chat box, how is your preparation going on? First answer received by Arpit is A. Arpit is A. Geometrical isomers. A, how will it show? With a geometrical isomer 2-methyl pent 1-ene. How will it show? It will not show. B, C, B, D, C, G. Okay, I've received several answers. Better try to draw the structures first. Don't just give me the answers out of thin air, right? Try to draw these structures. Try to draw the structures, right? If you draw the structures, let us draw the structure of the correct answer is 4-methyl pentene. How should I draw the structure of this? So pent means 1, 2, 3, 4 and 5, right? At the second position, there is a alkene molecule, and at the fourth position, there is a methyl molecule. So will this show geometrical isomers? Yes, this will definitely show. Hence, the answer is 4. Okay? None of the other compounds will show. You just have to draw these compounds, and then only you will know the answer. Yes, D is the correct answer. Whoever wrote A, let me draw the structure of 8. A will be pent 1-ene. So 1, 2, 3, 4 and 5, right? At the first position, there is a ene molecule. Okay, understood, understood. So here at the first, there is a ene. Can you see that here 2 hydrogens will be present? Can you see that? Can this show any geometrical isomerism? No, because these two compounds have to be different. These two atoms have to be different in order to show geometrical isomerism, isn't it? So this cannot show. This also pent 1-ene again cannot show. This is 2-methyl pentene. It becomes a symmetrical compound. Again, it cannot show. Only D can show geometrical isomers. Right? Right? Okay? So this is how it will show. This is the trans version. Trans means what? One of the alkyl group is here. The other alkyl group is here. So this is a trans version. This is the alkene. This is a cis version where both the alkyl groups are below it, right? So trans and cis both kind of is possible. Now let us talk about the optical isomers, which is your optical isomers depend on what? Depends upon on the carbon. Which carbon shows optical isomerism? Once again, that the carbon should be first of all sp3 hybridized. Understand this thing. The carbon should be sp3 hybridized, only then it will show your optical isomerism. Okay? And all the atoms attached to the carbon should be different, right? So the presence of a chiral atom means what? The carbon must be sp3 hybridized and all the atoms present around the carbon must be different, right? Different, hence it is called a chiral atom. And the entire molecule should have no symmetry in it, okay? And then the molecule that you're getting should be non-superimposable, which means if I make a mirror image of that, then they should not superimpose on each other. That is what optically active compounds are, okay? And these are of two types. For example, enantiomers. Enantiomers are what? These are mirror images of each other. Okay, here can you see the chlorine is attached on the front side, the mirror image the chlorine is attached on the back side, right? So this is what an enantiomer is like. Similarly, in diastereomers, what happens, bacha? Just the attachment of chlorine atoms is different. Can you see? Here one chlorine is on the back side, the other chlorine is on the front side. Okay. In the other carbon, what is happening? Both the chlorines are on the front side. Hence, these are not mirror images. This is not the opposite of that, right? If that had to be, what should be the mirror image of this? The mirror image of this compound should look like this. This is the chlorine, this is the chlorine. Isn't it? This is the mirror image of this compound, not this. Okay? Understood this, everybody? Everybody, these are diastereomers. Diastereomers are what? Which have the same exact chemical formula, same connectivity, everything is same. Just that arrangement of atoms in space is different. Hence, these are diastereomers. But these two are mirror images. Hence, these are enantiomeric compounds. Okay? For example, you can look at more examples of enantiomers and diastereomers. And what are meso compounds? Let us first understand them. But in meso compounds, what is happening? Look at this carbon over here. This carbon is satisfying all the conditions of a chiral carbon, which means this carbon is sp3 hybridized. All the atoms around this carbon are different, isn't it? This is also different, right? It is following all the conditions. But what is happening within this compound? There is so much symmetry is there. See, CH3, CH3, Br, Br, H, H. Can you see? There is so much symmetry is there. There is so much plane of symmetry present. Hence, whenever there is symmetry in the compound, that such compound is called a meso compound. And meso compounds are optically inactive compounds. Please keep this in mind. What is happening? These are meso compounds which are optically inactive compounds because they have symmetry in them. Okay? And we have already discussed what are enantiomers. This is another example of that for you to understand. I am moving forward. Right? Okay? Now answer this question for me. The question is on your screen. The number of stereoisomers possible for 1,2-dimethyl cyclopropane is again another wonderful question, and such questions are very easily asked, very commonly asked in your JEE exam. This is JEE Mains 2021 question. Try to answer this. Stereoisomers possible for 1,2-dimethyl cyclopropane. Try to draw the structure. So what does cyclopropane look like? Is this a structure of cyclopropane? And at the 1 and 2 position, there are 2 methyl groups. CH3, CH3 over here. Here's the H group, here's the H group. Can you see if I draw this structure? This is the cis molecule, isn't it? This is a cis molecule, and cis molecule actually has a plane of symmetry in it, which means this is a kind of a meso compound, which means this is a cis molecule, meso, optically inactive. But I can draw the trans structure of it. The trans structure will look like this. Here the CH3 will come and the next CH3 will be here. Isn't it? Isn't it? Now here there is no symmetry, but it will show us another kind of compound. This can show the mirror image of each other, right? Here the CH3 will come, here the H will come, here the CH3 will come, and here the H will come. So these two are what now? These two are enantiomers, right? So what is happening? This is the cis compound, this is the trans compound. And the cis compound has no mirror image of each other, while the trans compound, being optically active, will show enantiomerism. Now to answer how many stereoisomers are there, can you count? These are 1, 2, 3. 3 stereoisomers are present, 1 cis and 2 trans structures possible. Yes, the correct answer is not A, bacha, it is 3. 3 stereoisomers, because geometrical isomerism is also a kind of stereoisomers only. Na? That's what we're studying right now. Both are stereoisomerism. They haven't asked you the optically active compounds. They've asked you the stereoisomers. Geometrical isomerism is also coming under the stereoisomerism only. Right? So the correct answer is 3, as I've just told you. Right? Understood? Now try to solve this question for me. Which of the following molecules does not show stereoisomerism? Can I give you this homework? Can I give you, this is the second homework, right? I don't want to spoon feed you. Try to just pause this, take a screenshot of this question, try to attempt this on your own, right? So that you understand how do I look for stereoisomerism in general, right? Right? Okay, I'm moving forward. The answer is already given for you too. Now we're also going to learn about the RS nomenclature in the optical isomerism, right? In optical isomerism, there is a kind of RS nomenclature which is there in your course. Many times questions are asked from the RS nomenclature. Okay? This is shown by those optically active compounds. Remember that thing. For example, let us look at this compound. How do you give the RS nomenclature to anything? So first of all, let me tell you what is RS nomenclature actually. So RS nomenclature na, what do you think those compounds actually give which are optically active? Number first, they should be chiral. There should be a chiral carbon, which means the carbon should be sp3 hybridized. All the atoms around the carbon must be different. There should be no symmetry present in that. Only then such compounds will show RS nomenclature. Is this thing clear to everybody? Now what will happen? How do you determine the RS nomenclature? Do you see the carbon over here? Right? Here the carbon is attached to chlorine, bromine, hydrogen and CH3. So now the number first rule is to actually give these numbers. All the atoms are attached to carbon based on their molecular mass. Here the most heavy atom is bromine or their even atomic number. Okay? For example, bromine has the highest atomic number, followed by the chlorine atom, followed by the CH3 atom, right? Followed by the hydrogen atom, right? So I've given them all their numbers. Is this thing clear to everybody? Bromine, chlorine, carbon and hydrogen. According to the atomic number, I've given them numbers. Now next thing is what, bacha? The hydrogen should be at the dash position. Understanding this thing? The hydrogen should be at the dash position. Now the next thing what you have to do, you just have to rotate from the, this is the first thing, right? This was the first number, this was the second number given and this was the third number given. Okay? So when the hydrogen is already at the back position, you just have to move your pen in such a way from first to the second number of atom. So can you see when I'm moving this from first to second, what direction am I achieving? When I'm moving from first to second, what is this direction? Is this a clockwise direction or anti-clockwise direction? This is how the clock moves, right? So this is a clockwise direction, hence this here the carbon will get the R as the nomenclature. Understood? Because you have to move from first to second. That is it. So this gets the R nomenclature. Now let's see on the B part. On the B part, what is happening? Can you see? Here once again, bromine gets the number one position. Then the chlorine gets the number second. Now I have to move from first to second once again. Now in which direction am I moving? I'm moving in this direction. This is a anti-clockwise direction. So this carbon over here will get the S configuration. Is this thing clear to everybody? You just have to move your pen and determine if it's moving in right side of direction, clockwise direction, then it is going to get the R configuration. Otherwise, it's going to get the S configuration, right? All other steps are mentioned over here that you can just go forward, that you can just look for. Okay? Next is, how do we determine R and S when the hydrogen is not at the far away position? I just told you that the fourth atom, the most lightest atom, should be always at the dash position. That we're going to follow that rule. But what happens when your hydrogen is not at the dash position, but instead is at the is not at dash position, is instead at the wedge position? Everybody see that? Now what will happen? Now again it is very, very easy. Here what will happen? Try to again give numbers to these atoms. Fluorine gets the number 1. because it is the most highest atomic number, then oxygen, then your carbon, then your hydrogen. So I've numbered them. Now I know that OH, H is not at the dash position. Now try to move again from 1 to 2. So when I'm moving again from 1 to 2, what kind of direction am I getting? This is a, once again, anti-clockwise direction, isn't it? Isn't it? So what will happen, because the H is not at the dash position over here, here the configuration actually reverses from S to R. So R is the correct configuration. Why? Because H here is not at the dash position. Are you understanding this thing? So when in the previous example, the H was at the dash position, and when we were moving from 1 to 2, the exact, if it is moving clockwise, then we're giving it R number. If it is moving anti-clockwise, we're giving it the S configuration. But when the hydrogen is not at the dash position, but at the wedge position, what is happening? Then, bacha, we are moving it, then whatever direction we are getting, then we are actually reversing that direction. For example, when I move from 1 to 2 to 3, the direction I'm getting is anti-clockwise. So I will reverse it because the hydrogen is not at the dash position. So the correct configuration comes out to be R. Is this thing clear to everybody? Okay? So these are few more examples that you can look for. Next is the conformational isomerism. Again, very important kind of isomerism asked every time in your exams. So, bacha, what is happening over here? Can everybody see? Can everybody see? Here, these are called the conformational isomers, right? These are also known as rotamers. Why? Because these are rotating amongst each other. Okay? For example, these are the conformational isomers of butane molecule, right? So what is happening in this case? I'm once again telling you. First of all, how many conformational isomers can be there? They can be infinite, right? Because the angle keeps on changing from 0 to 0.1 to 0.001 to 0.00001, from 1 degree, 2 degree. By how many angles only, right? It is dependent upon you by how much angle you want to increase or decrease the angles, right? So how many conformation isomers are possible? The answer to that is infinite number. There can be infinite number of conformation isomers possible. Number first thing. Now, bacha, what is happening when two CH3 are right behind each other? Then the angle between them is actually 0 degree, and hence such a conformation isomer is called a fully eclipsed isomer, which is very, very unstable. Unstable means it has very, very high energy. Similarly, the next isomer is at the 60 degree angle. 60 degree angle, can everybody see? The angle between two methyl groups is 60 degree. This is called the Gaussian configuration, also known as the staggered configuration, where the methyl angle is 60 degree. Similarly, the next is once again an eclipsed conformation, where the CH3 and H are right behind each other. Here what is happening? The angle between the two methyl groups is actually 120 degree. This is eclipsed position. In fully eclipsed, the methyl angle was 0. In the eclipsed position, the methyl angle is 120 degree. Now in the anti-staggered position, what is happening? The two methyl groups are 180 degree apart each other. This is the most stable configuration. This is the most stable configuration. And all these rotamers, bacha, are very, very interconvertible to each other. These keep on converting into one another because the energy difference between each of them is very, very low. Okay? So these are interconvertible into each other. Next thing is there can be presence of infinite number of rotamers possible. Is this thing clear to everybody? Okay? Okay. Okay. Next is, this is how their energy diagram would look. Look at this energy diagram, every one of you. Right? Look at this energy diagram. Next thing, next question on your screen. Try to answer this question for me. Arrange the following conformational isomers of normal butane in order of their increasing potential energy? Who can answer this question for me? Try to answer this question for me. Arrange the following conformational isomers on the basis of their energies. We just discussed the energy order, right? Try to answer this question for me. I'm looking at the chat box. Just 30 seconds for you to answer. Now, first of all, see, here the two methyl groups are 180 degree apart. Here the two methyl groups are 60 degree apart. Here once again the two methyl groups are once again 360 degree apart, right? 60 degree apart. Now answer this question for me. First answer received by Dr. DD as C. Wow, what a name. Idea has answered C. Soumya has answered A. Monisha has answered D. Okay, Vidya has answered B. Harish C. Let us look at the correct answer. The correct answer is D. So whoever answered D, which is Monisha is very, very right about it. So let us see D. Here second bacha is in order of the increasing potential energy, which has the highest energy, which will be the least stable molecule. So can you see the second molecule? This is a very, very eclipsed structure. Right behind each other, everything is present, right? Next is your fourth option. Here fourth, what is happening? Here the CH3 is right behind the hydrogen atom. But here the CH3 was right behind CH3. So more steric repulsion. Here the CH3 is behind hydrogen, so less steric repulsion, but still it is unstable. So second followed by fourth. Then your third, why? Because here it is again 60 degree apart. And your first is the most stable because CH3s are 180 degrees apart. Everybody understood? Potential energy will depend upon the stability. More the potential energy, lower will be the stability. Because highly stable molecules have the least energy. Understand this? Okay? Have the least energy. Whoever answered D is absolutely right. Try to answer this question. In the following structures, which one is having staggered conformation with maximum dihedral angle? Who can answer this question for me? In the following structures, which one is having staggered conformation with maximum dihedral angle? Very, very easy question. Because these questions are repeated every now and then. That's why I've included them. Very easy question once again. B. Idea has told me B. Very good. Whoever has answered B is extremely right. Can you see here? The dihedral angle is 180 degrees. Hence, this is the answer. B is the answer. Very, very good, everybody. Extremely good, extremely good. Okay? Chalo, next question is on your screen. Choose the halogen which is most reactive towards SN1 reaction in the given compounds. Who can answer this question for me? This is a very amazing question. SN1 reactions. Now we're talking about SN1. What are SN1 reactions, bacha? Where there is a formation of carbocation, isn't it? SN1 reactions are two-step reactions, where in the first step, carbocation is formed. In the second step, the nucleophile attacks. Right? So SN1, we will consider the formation of carbocation. So here, choose the halogen which is most reacted towards SN1, which means what? Which will create the most stable carbocation. Answer this question for me. Very beautiful question once again on your screen. Very, very beautiful question. So I've received Lakshmi has answered D, Vidya has answered B. Beta, in every situation you have to answer. For example, A, which bromine would be better leaving group? So can you see if this bromine leaves from the A, which is the bromine A, if it leaves, it will create a benzylic carbocation, right? When this bromine leaves, it will leave a benzylic carbocation, isn't it? So bacha, this is bromine A over here. Will be more SN1 reactive. Similarly, Look at the B option. In B option, which iodine will be more reactive? Can you see if iodine A leaves, this will leave behind a carbocation over here, which is a allylic carbocation. Can everybody see? Allylic carbocation is made. Hence, here once again, A is better than B. A will show more SN1 reaction than B. Now, similarly, in C, bacha, what will happen? In C, once again, the B will leave. The bromine at the B position will leave and the positive charge will be made over here, which will be more stable. Because any positive charge at the bridgehead carbon, can you see this is the bridgehead carbon? This bromine is at the bridgehead carbon. So, any carbocation or any sp2 hybridization at the bridgehead carbon is not possible. This is very, very unstable. So, positive carbocation will never be formed at the bridgehead carbon. So, here again B is more reactive than A. Understood this thing? Now, let us look at D. D, bacha, what will happen? D, bacha, again this bromine A will leave and this will create a tertiary carbocation. Hence, once again, A is more reactive than B. Did you understand what I'm trying to say? Everybody understood what I'm trying to say? Okay? Here what you have to look for, which bromine will be easier to leave, which means according to the SN1 reaction. In SN1, we know there's a formation of carbocation. So as the leaving group will leave, it will leave behind a carbocation there, right? So you will follow this order. Is that everybody understood this, bacha? Everybody understood this? Shall we move forward? Chalo. Because in first case, that's a similar thing explained here. It is the benzylic carbocation, then the allylic carbocation, the non-bridgehead tertiary carbocation, then tertiary carbocation. Right? Chalo. Next question again from the SN1 reaction. Rate of SN1 reaction for the following compounds is. Again, what we're talking about SN1, which means formation of carbocations. Try to answer this question for me, everybody. Everybody. So, where will the formation of carbocation be more easy? Okay? Here once again, can you see when this iodine will leave, it will leave behind a positive charge here. When this iodine will leave, it will leave behind a positive charge here. When this iodine will leave, it will leave behind a positive charge here. Once again, a positive charge here. Now, let us see the groups attached to this benzene ring. This methoxy group is what kind of group at the meta position? Can you see this is present at the meta position according to the alkyl group over here? So, at the meta position, this methoxy group actually shows just one effect, which is the -I effect, right? Because oxygen is more electronegative. It will pull electron towards itself. Remember this thing. Similarly, your methoxy group over here at the para position will show the resonance effect, right? It is showing the +R effect, isn't it? It is increasing electron density in the ring. Similarly, the CH3 group over here will show the +I effect, which is again increasing electron density in the ring. Now tell me, what should be the SN1 order? What should be the SN1 order? Where will the carbocation be more stable? So if I'm positively charged, I want more species which give me electrons so that I become stable, right? So which is giving it more electron? So I can see that resonance effect over here is more effective than the inductive effect. I just taught you that order, right? Ki aromatic, then resonance, then comes your hyperconjugation, then comes your inductive. So here now you can compare both of these effects because resonance effect has the more priority order than the inductive effect, hence this will be the answer. Okay? So this carbocation will be more stable. B will be the most stable carbocation, followed by the C carbocation, because this is once again giving electrons to this carbocation. Okay? Now bacha, followed by what? Followed by your D, then followed by your A. Because A is doing what? It is decreasing electron density in the ring due to the -I effect of the methoxy group. So the correct answer is B, C, D, A. Is this thing clear to everybody? Correct. Very, very good. Very, very good. Nikhil is correct. Nikhil is correct. ठीक है? Understood? Understood? So this is again explained over here. Now let us solve some many questions. So I have compiled a list of reagents. I'm so excited now. I'm so excited to solve these questions with you guys. What is the major product formed by HI on reaction with this molecule? So whatever reagents I have accumulated here are the most asked reagents, will definitely be asked. Every time they're asked. So this year also they'll be asked in your shift. So first is, which is the major product formed by HI on reaction with this alkene? Who can answer this? Very easy question. Very easy question. You have 4 options with you. 4 options with you. 30 seconds to answer. 30 seconds to answer. Try to answer this question. And now my laptop is going to switch off. Chalo. First answer is C by Shubham as A, Vidya as A, Nikhil as A. Very, very good, everybody. A answer. Whoever is giving me A answer is absolutely right. The correct answer is A. What will happen in this case? This is the alkene. The alkene given to you is CH double bond CH2. Here is the C present over here. Here is the CH3. CH3. Here is once again the CH3 molecule. Right now when the HI reacts, HI means what? It will get converted into H plus and I minus ion. Okay? Now this alkene is electron rich. So it will attack this H plus over here. Isn't it? It will attack it here. Now what will happen? The hydrogen gets attached here and the positive charge actually comes over here. And now your double bonds gets converted into a single bond. Isn't it? This is the first step. Now the second step, can you see that there can be a 1,2 methyl shift that can happen? Because here this is a secondary carbocation. I can convert it into a tertiary carbocation like this, CH3. Here I can become a positive charge. Here C, H, here is the CH3 and here is the CH3 once again. Now to this positive charge, this negative iodine will attack over here and the final product that you're going to get is the A answer. Understood? Very easy and almost every time asked question. Very, very common question this is. Okay, so you should know 1,2 hydride shift, 1,2 methyl shift because one question is essential that will come in your exam. Now let us look at this question. The major product of the following reaction is, who can answer this question for me now? Yes. The major product. Try to answer this question for me. The major product of the following reaction. So here you have a benzene ring and you're trying to react it with this molecule. Right? Try to answer this question for me. What will happen, bacha? Try to solve this question. Here what will happen? You have a acid again with you. So what reagent do you have? You have a NO2 over here and a alkene over here, right? And you're trying to react it with a H plus, which is a acid given in your question. Now what is the first thing that should come in your mind? Ma'am, there is an alkene and an acid. So the alkene will attack the H plus and I will get what kind of carbocation? That is the trick over here. The trick is what kind of carbocation you will get. You will get 1, 2, 3. Here is the NO2 group, right? And here come the positive charge and here the H will attack. So what I'm telling you is here in this case, primary carbocation will be more stable. Here I haven't made secondary carbocation. Why? Because can you see NO2 group is attached over here. NO2 is a electron withdrawing group. Hence, the positive charge, if it comes on here, this NO2 group is destabilizing that positive charge, right? So, in this case, due to the electron withdrawing group, primary carbocation will be more stable. Understood this? So, here this carbocation is formed. Now, I'm trying to react it with benzene molecule. Now, what is the feature of the benzene molecule? Benzene molecule, bacha, is a very, very electron-rich species. Understand that. It's a very electron-rich species. Hence, this will attack this positive charge over here. So, the final product that you will get is a benzene ring and a structure like this. 1, 2, and 1, 2, 3, 4. 1, 2, 3, and 4. Right? And here is the NO2 group. Right? So, this is a structure form. Sorry, NO2 group is here, not here. Okay? So, the final structure formed is the B compound. Right? Understood this? Understood this, everybody? Everybody understood this? So what did I do? You have to look at the reagents. I have an alkene with an acid. So acid and alkene will do what? Form a carbocation. Then the benzene ring is an electron-rich structure. Hence it will attack this carbocation, and this kind of structure will be your correct answer, which is the B option. Understood? So what I'm teaching you here right now is how to approach the reagents and not get scared of them. So whatever reagents I've chosen are the scary ones. You don't know how to approach them because these are not name reactions. Because name reactions you're very familiar with. You have all rectified all the name reactions. But these reagents, these basic chemistry reagents are the beauty of organic chemistry. So learn with me right now. Try to move the arrows with me and you will love. You will fall in love with chemistry in this hour. In this hour, try to do. Next question on the screen. For the given reaction. So again, you have an alkene with the bromide molecule. You're trying to react it with NaNH2 and then red hot iron tube at 873 degree Kelvin. What will happen? What is NaNH2? This is sodamide. Sodamide is used for what? Sodamide is used for making this product into an alkyne product. So this is a reducing agent once again. So what am I doing? With sodamide is a very, very good reducing agent. So what it will do? It will do CH triple bond CH will be the product, and then here it will be the CH3, right? So with sodamide, what am I getting? I'm getting an alkyne product. I'm getting an alkyne product with sodamide, right? Okay? Sodamide has done what? It has taken away HBr from the molecule. Okay? Now what is the next thing? Red hot iron tube. This is once again a very important reaction given in your hydrocarbons chapter. What is the function of red hot iron tube? It converts acetylene into aromatic benzene ring. Understand? It converts acetylene into aromatic benzene ring. But here we have a derivative of acetylene, right? Of ethylene, we have a derivative. So it will also convert this derivative acetylene. For example, this will be converted into benzene ring. I understand that, ma'am. Now, ma'am, what will happen to this CH3 group? This will also get it triple time. Triple time means what? One CH3 here, one CH3 here, one CH3 here. Right? So this will be the final product formed, which is your mesitylene product. Mesitylene product. So first of all, the function of sodamide is to convert double bond into a triple bond. Next is red hot iron tube does what? It converts the ethyl, this acetylene structure, into a benzene ring. Understand this. Okay? So this is convert this two carbon structure into a 6 carbon structure, which means it is what doing? 3xing the number of carbons. Now you have been given in your question a derivative of acetylene. Derivative of acetylene will get converted into the derivative of benzene, and this CH3 will also become 3 times of its number. Understood this? Understood this, everybody? Very easy question once again. Yes, the correct answer is C. Everybody who's answered C, very good, extremely good. Next question on the screen. Again, I'm going to teach you how to solve this reaction sequence. What you have been given? You've been given a molecule C8H10. What will be the structure of C8H10? I think C8H10 should look like this. A benzene ring and a CH2CH3 CH3 group, right? This is the C8H10 molecule. You are reacting it with HNO3 and H2SO4. What is that? That gives me the nucleophile NO2+, right? This is the nitration reagent. Where will the nitration happen? When I give it the NO2 plus electrophile, nitration will happen on the benzene ring at the para position, isn't it? So the nitration will happen on the benzene ring CH2, CH3 at the para position. Why at the para position? Because this alkyl group is actually ortho-para directing, with para being the major product. Now next is you're reacting with bromine and heat. Okay? In presence of bromine and heat, what will happen? Where will the bromine get attached now? Bromine gets attached here. When I'm reacting it with bromine and heat, the bromine gets attached on this benzylic carbon. So here the bromine will attached. Understood? Understood. Next is you are reacting it with alcoholic KOH. Alcoholic KOH does what? It is famous for elimination. So alcoholic KOH will just remove HBr. What it will form? After reacting it with alcoholic KOH, it will remove minus HBr from the molecule, and the final structure that you're going to get is looking like CH double bond CH2, and here will be the NO2 group. Simple. So the correct answer is B. Correct answer is B. Whoever, wow, I've already gotten so many B's. Very, very good, bacha. Very, very good. Whoever answered B is extremely, extremely right. ठीक है? चलो. ठीक है? Understood? Easy peasy questions. First of all, nitration happens at the para position. Then with bromine and heat at the benzylic position, the bromine gets added. Then with the alcoholic KOH, elimination of HBr happens. Always remember, with alcoholic KOH, there will be formation of an alkene, right? With alcoholic KOH, alkene gets formed, so HBr gets removed. And this is the product that you're getting. And which kind of alkene? Most stable alkenes. Okay, try to solve this question. Among the following, the major product of the following reaction is. This is once again JEE Mains 2022 question. See, such kind of questions are asked which checks your basics of chemistry. So I'm going to teach you how to approach such questions, right? So can you see the compound given to you looks like this. Here's the oxygen, here's a double bond, and you're trying to react it with Br2 in presence of CH3OH, right? Now can you see a double bond is there? Okay? A double bond will do what, bacha? The Br2 first of all will get attached. So bacha, to this double bond, first of all, here's the oxygen. Here the Br will get attached. Okay? For example, if I attach the Br, for example, at the back position. If I attach the Br at the back position, which means what? The positive charge will come over here. Isn't the positive charge stable over here? Why? Why is the positive charge stable over here? Due to the lone pair of electrons are present, and hence it can undergo resonating structures, right? And to this positive charge, what will happen? The electrons from this ethanol will attack. Now, bacha, this attack will actually be from the front side, right? Because Br and CH3OH. So whenever you're adding bromine, right? I'm also telling you one more thing. So whenever you are adding bromine in presence of any protic solvent, which means any solvent which is polar and gives out H plus ions. It can be water, it can be ethanol, CH3OH, right? It can be anything. If you're adding bromine under these circumstances, then the addition will happen on this alkene, right? Addition will happen on one carbon, bromine will be added, on the other OH will be added if you have taken H2O. But here, because you have taken CH3OH, so on the other carbon OCH3 will be added, right? And how it will be added? As the anti-product. Anti-product, which means what? If the bromine attacks from the back, then the OCH3 will attack from the front. So here the only correct product that seems to me to be correct is actually the A product, right? OCH3 will come near to the carbon of oxygen, near to the atom of oxygen. Here the OCH3 will attach, and these two should attach from the opposite sides, which means if Br is attacking from the back, then the OH3 must and specifically attack from the front side. Is this thing clear to everybody? Yes, the correct answer is A. Understood? So whenever you are attacking bromine with either water or ethanol or any protic solvent, then the addition is anti-addition, first of all. And if you have taken water, then OH will attach over here. But because you have taken methanol, then OCH3 will attack over here. Understood? I'm moving on to the next question. The major product formed in the following reaction. Once again, similar type of question as we have done earlier. Here what they have given? They have given you an alkene, and also they have given you bacha a OH group. Now bacha, where will this H plus first attack? Will it be first attacked by the alkene? Because alkene can also take the H plus, but the lone pair of electrons on oxygen can also take the H plus. Now there is a competition between the two, isn't it? Now who will win this competition? That is the question. So bacha, always remember that the lone pair of electrons are always more, because these are so electronegative. So that will definitely abstract the proton more towards itself. So the first will be what? The first thing that would happen. Okay? This is the first thing that could happen. Right? Okay? Like the conscious mind says that. But again, understand another thing. What if I do this? What if I do this? Here's the oxygen atom, right? Here's the double bond. Now what if I do? What if I attack this double bond on this H plus? What will happen? The H will get attacked over here. The plus will get attacked over here, right? Now can you see this plus? This plus over here is actually resonance stabilized due to the lone pair of electrons on this oxygen, right? So this is actually a stabler carbocation formed. Even though I'm still saying that if you have a competition between the OH group and the alkene, the OH will definitely attack H plus first. But then you also have to see if alkene is forming a very stable carbocation, just like this, then that would be formed in such a case. So this carbocation is formed. Now what will happen to this carbocation? This oxygen will now attack. So the final product formed will be to this carbocation, this will attack, which means D is the final product that is formed, right? So this oxygen will attack this positive charge over here, and the D product will be formed in the final case. Correct? Understood? Correct? Understood everybody? ठीक है? Chalo. Next question. The major product in the following reaction is. The major product in the following reaction is. Who can answer this question for me? The major product in the following reaction is. We're gonna take this as the last question. It's already around 12, right? It's already, I guess, 11:50. This is going to be the last question. Very, very easy question, right? This is again a very easy reagent. In this reagent, what is this? This is my oxymercuration, demercuration kind of reagent, isn't it? Isn't it? Should I give you as homework? Should I give you this as homework once again? Everybody who is watching me right now, yes, bacha. So what will happen? The OH will, in oxymercuration, demercuration, what is the first step? Okay, I will tell you, some people are still interested and not sleepy. So I will tell you, so this is the structured form. This is the alkene. Okay? So in oxymercuration, demercuration, according to the Markov-Nikov rule, OH is attached here and the H will be attached here to the double bond. Okay? OH will come here, H will come here. So that is the first attachment. And there is no rearrangement possible in oxymercuration, demercuration. But what will happen with NaBH4 now? So the correct answer is just this, because NaBH4 is once again what? Sodium borohydride. It's going to do hydration only. So after hydration, you're going to get the OH product like this. So the correct answer is actually A. You don't have to do any other thing. You don't have to oxidize or do any other things. Correct answer is A, because this is just giving you the hydride molecule which will be taken away by the oxygen atom, and that's how you're going to get the OH product. Correct? Correct. Now this, okay, this is the last question, because I love this question. This is the major product for the following reaction is. Okay, now you have to predict the major product. I'm drawing the structure. This is the alkene, right? And here is the C triple bond N atom present over here. Okay? And you're trying to react it with OH and 1, 2, 3 SH group. Right, bacha? Now what will happen? Can you see these are electron donating groups? So I need to look for that thing which is electropositive in this case. Can you see this carbon over here? Because nitrogen is more electronegative than carbon. So nitrogen will get a delta negative charge. Carbon will get a delta positive charge. Now, which of these both will attack? So can you see oxygen over here also has lone pair of electrons. Sulfur over here also has lone pair of electrons. Now, which lone pair of electrons will attack this delta positive carbon? So, bacha, here just look at one thing. Oxygen is more electronegative. Hence, it will keep the electrons to itself. It will not let it go away. While sulfur is more it's less electronegative. Hence, it will easily donate the electrons. Hence, these electrons will now attack this carbon over here. Okay? So, this would be the final product. Here, what will happen, bacha? Here, what will happen? This is the double bond, and this is this, and this is the C, and here the S, C double bond N, and here will be the S will be there, right? So, this is how this will get attached. Okay? So, which do you think is the answer to this? Which do you think is the answer to this? Do you think D is the answer? D is the correct answer? Correct? Correct. Whoever answered D is absolutely right. That would be the correct answer. Okay? Understood this thing? Chalo. Next is decreasing order of reactivity towards electrophilic substitution for the following compounds. Homework question. I'm not doing any more questions. It's already 12 a.m. I wish you all the best, right? So whatever other reagents I had in my mind, I'll actually provide you the PDF. You can take help through that. And if you still have questions, if you still have doubts, ma'am, I cannot understand this, cannot understand that, then for these 3 days, right, till your exam, you can connect with me on my personal Telegram channel, which is Nandini JEE. I will try my best to answer most of the questions that you're going to ask on this channel. Because right now, this is a newly created group I created 2 days back, right? So only a few students know about it. So if you post questions, you can post your screenshots of the questions, or you have any doubt regarding anything, you can ask me on here, where I'm available almost all the time, except when I'm sleeping, right? Also, I was not available for a few, like for yesterday, because I was not well, as you can tell from my face. But you can reach me out on my Telegram channel. Find me at Nandini JEE. Let's connect. Let's get to know each other. And thank you for attending the session. If you have any doubts, feedbacks, positive, negative, let me know. Let me know, my bacha. Okay? Chalo. Good night, everybody. All the best for your exams. I will definitely come back with more packs and surprises for you, which are going to be helpful. But these, right now, I've been creating all these stuff just to give you guys, spoon feed you before your exam. So tomorrow, there are more surprises for you guys. Wait for that. Till then, good night. Bye-bye. Thank you for attending. Let me end the